Welcome to the first tutorial of DVCon, Efficient Portable Programming Sequence Development with PSS. I am the General Chair of the conference. I welcome you all on behalf of the steering committee as well as everybody else involved in putting this on. In the Portable Stimulus Working Group, I am the Vice Chair. I will be introducing some of the other members as we go through this, and we're going to have some Q&A at the end. So let's get started. First, my friend Adnan Hamid from Breaker is going to give us some of the motivation behind portable stimulus. Why are we bothering to do this in the first place? A lot of good reasons and some really good data that we have that will show you why this is important and why you need to learn, which is why you're here, which is great. I'll do a quick introduction to PSS, the language, some of the features, some of the benefits that you'll get out of it from there. Matthew Balance, who was just voted to be the new chair of the working group from AMD, is going to talk about developing reusable test content at the block level. Then Sergey Hyken from Cadence is going to talk about subsystem and SoC-level testing. Then Prabhat Gupta from AMD is going to talk about post-silicon testing. And then I'll come back in, talk about some of the new features and some of the plans that we have for portable stimulus going forward. And then we'll have some Q&A at the end. So we'll not only have the presenters come up, but other members of the working group that are here will come up for the Q&A, and we'll answer your questions at that point. If you do have questions as it comes up, you can raise your hand and let us know that you have a question. We have a mic down here, so everybody will be able to hear your questions as well. If you want to just shout them out from the back of the room, we can just repeat the questions for everybody, and we'll go from there. So, all right, without further ado, I will bring up Adnan Hamid from Breaker.
Thank you, Tom. How many people here are doing verification with UVM? Show of hands. Everybody. How many of you think you're working on relatively complicated blocks with UVM? Actually, fewer than I thought you would say. Oh, a bunch of you are doing simple UVM work? Okay. How many of you do UVM where you can get your entire project done with less than 10 UVM sequences? All right. You don't need PSS. You're out of here. How many are managing over 1,000 sequences that are needing to be ported from project to project? Nobody admitting to it? This is what I see every day. The question is, can we do better, right? We're not trying to remove UVM. UVM is here to stay. But UVM environments get very, very complicated. And can we make those environments simpler? And can we do it in a way that's reusable? Right? So this whole presentation was originally envisioned as a conversation about how can we keep from rewriting the same test content over and over again in a project. My name is Adnan Hamid. I'm founder and CTO at Breaker. So Siemens does these every 2 years, this a survey of everything verification, which is very helpful. And what does the data tell us? Right? We're all saying that getting good verification content is a very big problem for us. Right? Whether we're in UVM, whether we're in subsystems, whether we're in full chip, whether we're doing simulation, emulation, post-silicon, everybody's worried about content. When you look at where the design budgets go, right? How many people here are verification managers that are managing a bunch of people? Actually, a smaller number than I would have hoped for. Come on, Tom, we've got to step up our marketing over here. Anyway, those of us who are managing budgets, right? Data shows that about 30% of our budgets are going towards developing test content, another 25% debugging, which if I just tell you that data, you look at it and go, yeah, that feels right. But the problem is that much of that debug is debugging the test content and not the design itself, right? So that's over 50% of your flow that could be optimized. Those of you who are UVM engineers over here, you do your block level verification, IP level verification, hand off to some integration team. How many of you then get pulled in to subsystem integration, full chip integration, debug in post-silicon? Are you guys getting pulled on that later in the project? Right. The point is that the UVM IP verification engineers are the only ones who ever actually figure out the details of how each IP works. They're in the business of testing every corner case of it, right? But that information is locked up in a UVM environment, and there's no way for anyone to reuse it. So when somebody's trying to integrate your IP into a bigger system, they have to come to you and say, hey, help me understand how I'm really supposed to program this, because I did what I thought it told me in the spec, but it didn't work. All right? And then you go to them and say, yeah, the spec doesn't say it, but you really have to write this one bit, or you have to write this register before that register. And why do you know? Well, because we tested the other way and it didn't work. Okay, so there is key knowledge tied up that has been developed in these UVM IP benches We're the only ones, where's the thing that lights the light? Is it this? We're the only ones who understand the IP functionality completely. We are being pulled on to go up to the system level. The firmware guys, they also don't know how our IP works, right? They're also trying to understand what to do. And there are a few of us, right? By the time somebody's integrating something we verified, we're on to the next project, and we're really grumpy when they pull on us to help integrate a block that we worked on 6 months ago. What if we could take all that knowledge and put it in a form that was reusable, right? That could be synthesized to every level of verification. And that's really what the purpose of this tutorial today is. UVM is the way to do test benches, right? PSS is not trying to say no more UVM. That's not what our collective story is. This is how you get your commercial VIPs, right? If you need a PCIe VIP, you're going to go get one from Synopsys or Siemens or somebody, right? And it's going to have a UVM interface in System Verilog, and that's what we're going to use. UVM rel is well used. We have a config DBs. All of that is working well. But after the basic test bench is built, right, your interface VIPs, your config DB, and so on, UVM is not really, really helping us with the test content, right? What is a verification? A verification is proving that an implementation, your RTL, matches an intent. And we as DV engineers, we are all in the business of trying to define what the intent of a design was and trying to prove that the implementation does. Or, if you're a good DV engineer, prove that the implementation doesn't do what you think it should. Right? It's our job to break it. Okay. So when it comes to sequences, we're pretty much on our own. We've got to write those. When it comes to scoreboarding, we've got to go write our own scoreboards, especially dealing with things like error handling, concurrency, very difficult problem to solve. Coverage, we asked to go write a completely new model to go see, have we exercised all the corners? And there's RTL coverage of the implementation. This is good. We should keep that. But we also care about stimulus coverage. Have we done all the use cases? Not so easy to do. UVM gives us constrained random test generation. It is beautiful for generating random transactions. But random transactions are not enough for verification for us, haven't been for 20 years, right? The whole point of sequences is we are capturing different scenarios. We are saying we've got to write this register followed by this register to do something and to make something happen. And we all know that we're writing only some of the scenarios of the many, many, many sequences and concurrency cases that could be there, right? So what if we could find a better way to capture all of that such that something generates all those scenarios for us? In simple terms, I think of it as constrained random transactions, fine. They give me the individual transactions, but I need some way to do constrained random sequences. And that's what we don't have a good solution for. Okay, speaking again to the UVM engineers, all of us are good at launching a bunch of sequences concurrently, fork off a bunch of them, and allow them to randomly interleave with each other, right? This we can do. But actually trying to schedule concurrency that is resource aware to say, okay, this block can only do one operation at a time. I've got to wait for that operation to finish before I do something else on it. Take the output of one block, feed it into the input of the second block. What else do I have over here? Concurrency, the resource management, and memory management, right? So in UVM, we typically do our memory management pretty much ad hoc. We don't have a good way of scheduling memory for the operations. Yet, we're asked to do this every day, right? I see many, many UVM environments where there's some form of a malloc that is somehow trying to figure out what memory this next operation should use, and it's difficult to reuse that memory, difficult to share that memory. PSS is designed to solve a lot of these problems, okay? So let's say you're talking about a DMA example, right? It's common to do DMA in an IP environment. Well, what has to happen for all of that to work, right? We have to initialize some memory. Okay, you can do this in a UVM sequence, but in PSS, it's natural. You say, okay, a prerequisite to doing this DMA is go get me some memory that was initialized to something. Then I got to make sure I do only one operation on a particular DMA channel at a time. We can manage this in UVM with the right events and the right weights, but it's annoying, it's difficult, it's error prone. Over here, we can just lock a resource, and the PSS scheduler will know that I got to finish this operation before I carry on. Okay, DMAs move data from somewhere to somewhere. We can model that data flow. Okay, I have some input data, I have some output data. Okay? And then we need some constraints of the system. We know that, okay, the input data has to be, the input size and the output size have to be the same thing, so we can express those constraints. Anybody who's a UVM engineer knows how to do this in UVM, but compare how much work you have to do over there to what code has been written over here, right? So this is the beauty of why you might want to look at PSS. Okay. The biggest problem we have in the industry as a whole, as I see, and kind of the purpose of this tutorial, is we're UVM engineers. We put UVM on our resume. This is identity. This is what we do. We know all about what this IP does, but we are not good at helping our partners, our customers, reuse that knowledge at the next level up, right? Once you have individual IPs, somebody's building a subsystem, right, where presumably you took out the CPUs but put in all the other blocks of the design. You're trying to see where their IP end-to-end scenarios work. So in a subsystem, we might instantiate multiple IPs, and we want to check that we can do end-to-end scenarios. We want to know that data can come in off the modem, be moved by the DMA, and sent to the audio subsystem. These are hard to reuse in UVM. Yes, we can rerun the individual UVM sequences and make sure each IP individually is working at the system level, but it's hard to do end-to-end scenarios where the output of one move, one operation is the input to the next. So PSS will help you with that. And then we need to move up yet another level, right? Eventually CPUs go into our SoCs. We need software to drive these things. We possibly want to bring firmware in, but you were the guys who knew what the operation of the IP was, and all that information is locked up in your environment. And the whole story over here is if we can move that up to a slightly more abstracted model in PSS, which really isn't that different than UVM, and if you read through all the fluff, the actual use model for the language is really quite simple. Another way of looking at this, right, is one appeal is, hey, UVM engineers, you have all the knowledge, we need it for the rest of the company. The other one is you have all the knowledge and you're doing a lot of work. How many of you think your UVM environment is a bigger software development effort than the design implementation itself? Yeah. Does that make any sense to you? Okay. We'll build a UVM test bench, right? UVM is a beautiful thing. The interface VIPs will be there, config database, all the basic building blocks, that comes up. We need that. We're not trying to replace that. But on top of that, we start to write a lot of software, right? Trying to deal with events that are scheduling things, trying to fork a bunch of sequences that are trying to talk to one another, trying to manage memory, trying to manage scoreboards. One of my good friends who does a lot of UVM says, create constraint hell, right? We have no idea what's going on. And all that knowledge is caught up in that piece of software. If the first UVM engineer moves, it goes off to a different project, different company, really hard for the next guy to come along, pick it up, understand what's going on. Certainly impossible to reuse that knowledge upstream to the next level. The pitch very much is, right, that PSS plus UVM gives you a much more powerful solution. We can go look at our designs and understand the flows that the design is supposed to manage, right? We can think of them as data flow and control flow sequences of things that have to happen through our design. Specifically, we can represent these scenarios as UML 2.0 activity diagrams. PSS lets us capture those flows directly into a model, a high level of abstraction than what UVM lets us do. And then the whole point is the PSS tools can synthesize that model down to what your UVM environment needs. And that's the great beauty of this, right? Just like RTL synthesis took us above drawing gates and schematic capture, let us write RTL and generator gates. Maybe writing UVM sequences is like drawing gates, right? And moving up to PSS is like moving to RTL for test synthesis. As UVM engineers, why might you care? Okay? So for new test benches, folks are reporting in at about 50% reduced effort. Okay, so it is taking less work to write PSS models than to write the equivalent UVM sequences. And that's pretty much given that they're also trying to learn this new language along the way, right? The language really isn't that different. When you're going across generations of IP, right? When you go from version 3 to version 4 of the same old USB thing that you've been working on for the last 5 years, The reuse is even better, right? Some places clocking up to 75, 80% reuse. Much easier to port a PSS scenario than a UVM scenario. Yes, sir, back in the corner.
That first bullet point, is that literally for brand new test benches from the ground up, or does that infer some amount of reuse or leverage?
Yes, the question is this 40 to 60% reduction effort on a new test bench. Is it from scratch, or is it leveraging work that was done previously? And I think that's a really important and practical question, and for sure this is data coming off of not only from scratch, but from scratch on teams that are also learning PSS at the same time. Okay, so it's a big deal. And yeah, they're seeing that the man-months required to finish a project is really being cut in half, right? Whereas maybe there were 6 people tied up to do UVM before, they're doing it with 3 people. Okay. And yeah, UVM, we do a lot of repeated boring work, right? So all of that goes away when you move to a high level of synthesis. So that's your world, right? What's in it for me? What's in it for your customer? Once you have these PSS models, if you saw how we did that DMA example with the inputs and outputs, it's really easy to plug these models together, right? They're designed to model data flow and control flow across systems. And now we can combine those models to do system-level scenarios, and we can generate them for the full chip. So now instead of somebody having to go reinvent, hey, how do I do a DMA transfer? Reinvent how do I get data off the modem? Reinvent how do I send data to audio? They can take the work you've already done and move it up to another level. And in the big picture, I didn't even have any UVM managers over here, so I certainly don't have... Do I have any people who are actually full project managers thinking from UVM to subsystem all the way to post-silicon? Anybody thinking about the full projects? Okay. But if you look at it from the perspective of a VP of engineering, right, who's trying to get a product out, this allows us massive left shift of a verification, right? The idea is that we start writing PSS models for our IPs, mix them with pre-existing models, so-called system VIPs, to build a system model. And what are these models going to run on? Well, maybe early in the project, we have a virtual model in System C. Good, let's go run on that to make sure the virtual model is good. Then as the IPs are coming up in UVM, we can drive those. Then as subsystems get built, we go verify them, go to emulation, go to post-silicon. What platform are we running on? Make it a back office problem. As these platforms come up, we'll run on them. But the models, that's where the knowledge is. That's where your value is. And let's capture it in something that's reusable. So integration guys, right? They love this stuff, and we're going to see that story come over and over again in the next sections of this presentation, right? Much easier to understand what the IPs do. These PSS models are more abstract. They are a living document of what the IP is supposed to do. It's something you can understand. Much better coverage, of course. We're all worried about a system-level coverage. If you look at the data, chips are still late. Most of the bugs are coming about because we can't integrate our IPs properly because, frankly, we don't understand what our specs are, also coming out of the Wilson reports. A lot less work, right? The integrators, they have a tough life. They're trying to integrate 50 different IPs, and if they've got to go learn what each IP does, they have no hope other than to do something very lightweight. We wait until actual Linux boots and we do real software work on the system, and that's kind of late to find bugs. So that's a big deal. We can put much more stress on these designs artificially without waiting on actual software to come along. And for those of you who actually work in system validation, right, it is tough to get a system running full Linux with multiple processes running in addition to your workload to actually line up the difficult cases, right? They happen once in a million times. They fail once a week. This is our worst case situation, right? Bugs that happen once a week in running across a farm of post-silicon platforms. Over here, we can synthesize them the same as we do in UVM, random stable, and so on. We can replay them, reproduce them. If you have a failure, you can reproduce it in UVM, and so on. With that, I'll hand off to my good buddy Tom, who, of course, you guys have never heard of, right?
Nice job. All right, so what is PSS? So I am going to do something that I have actually never done before in public. I am going to explain a language without showing any code. All right, let's see if I can do that. Okay, so we're talking about a new way of thinking. Okay, this is one important thing about portable stimulus. The language itself isn't that hard. Understanding how to think about it is really the challenge, and it's really not that hard because once you start doing it, it just sort of falls out naturally. So what we used to do with System Verilog was we brought this new approach to verification, constrained random, right? So we went from directed testing, where we had one test per piece of code, and when you needed a new test, you had to write a new piece of code. Sometimes we could put some of those things as functions or tasks or whatever and reuse those, but it was still fundamentally a new description of what was going on. With constrained random, what we got to do was to write one test, one sequence, and rely on the randomization to get multiple scenarios out of that. The scenarios are very similar one to another, unless you want to put a giant case statement in the middle of it and all that kind of stuff, and that becomes really difficult to manage. So what we could do is kind of start at the beginning and go down this place, and as we add more constrained random, we fill out more things. Once you start randomizing stuff, you don't necessarily know what's going to happen, so we need functional coverage to know whether or not we might have hit this bug or not, right? So functional coverage is required for constrained random, because you don't know ahead of time what it is that you're going to test. That's really the difference in thinking. When we move to portable stimulus, we're now declarative. So we say, this is the thing that I want to have happen. This is my verification intent. It's a concise model, and it can describe a much larger set of tests because in addition to saying, this is what I want to have happen, you say, these are the rules for my system to figure out what has to happen to make this legal. So if I'm doing a DMA transfer, I want to transfer data from this area of memory to that area of memory. Well, it has to get into this area of memory first. How do I do that? Well, there's lots of ways of doing that. Right? It could come in from the modem. It could come in from the Wi-Fi, wherever. Right? You could type it in if you wanted to. Right? So there's lots of ways that that can happen, and we can figure out what it is that we need to do to make that happen. What are the data flow requirements? What are the constraints on the data? Right? If I say, in order for this to happen, to move memory from here to here, the data that I'm going to move is of a certain size, then it's only legal to put into there data of that size. Right? So if I have part of my system that can only generate really huge pieces of data, I can't pick one of those to supply that data. It's not going to work. Right? So I can define those kinds of rules as constraints on what my system can do. And then we allow the tool to generate the code to execute on the target platform. Right? How many of you have heard of Esperanto? Right? That was an effort to do one language for everything a long time ago. Right? Never worked, never could work, never can possibly work ever. Okay? So what we are doing here is we have said, we know we can't do that, but there are certain things that we can define that are common regardless of the target platform that you're dealing with. That's the abstract model. And then you supply the implementation for your target, and we can put those together, and we'll see kind of how we do that in a minute. So we have the abstract model, which is what does it do? And then we have the realization layer, which was how does it do what it does? This is what makes it real. That's why we call it the realization layer. So we wanted a concise language to specify that verification intent, and this is a complement to UVM. This is not a replacement for UVM. In fact, for those of us that do UVM, UVM is one of the ideal platforms on which to target your portable stimulus model. Right? The idea of UVM virtual sequences is probably going to be replaced by PSS. Everything else is still going to be there, right? Including the sequences that run on the sequencers and in the agents of your UVM model. Those are the things that make the transactions happen. Right? What we're going to do is coordinate the activity across all of those pieces. So if we think about a typical system here, so we have a UART. We have a UART agent, right? This is our UVM component that's the outside world. It's sending data into the UART. And this is our system here. It's an APB agent. It's going to set up the UART to make sure that it can receive the data, and it might do something with the data when it comes in. So we have to initialize the UART. We have to configure it. We have to configure the UART agent. We have to receive the data on the UART. We have to transmit the data from the agent. And then if we want to transmit data from the UART, we have to have the receive of the agent. Okay? So each of those actions, each of those behaviors is targeted to a specific component in our system. the schedule of how those things work. We're going to initialize the UART. The two configurations are going to happen in parallel, and then we're going to do a receive and a transmit from the agent, and then we're going to turn it back around. Right? So this is just a simple loopback test. That's the schedule. We call that an activity. Okay, you're going to hear these terms as Prabhat, Matthew, and Sergey talk about it. This is what we mean. When we have sequential data, there's this thing we call a buffer. It defines that somebody has to create the data in the first place, and then later somebody uses it. That implies sequential behavior. So this action can't happen until this action completes to create the data in the first place. When these two things are happening in parallel, we call this a stream. Right? So if I say I have a data stream, that means that there must be a producer and a consumer that are operating in parallel. Right? Because otherwise the data is going to get dropped on the floor. Somebody has to catch it. And then we also have state information. Right? Was my UART configured? Well, if it wasn't, then I better do an initialize to set it up. Okay? So we can define things like that as well. I didn't draw it in this picture because it would get a little bit too involved, but there's also this thing we call a resource. Right? So if in order to do a DMA, or for doing this transfer, I need some resource in the system, I can model that as well. So if I have, you'll see examples of multiple DMAs, right? So if my system has 4 DMA channels, for example, I tell it, those are the rules. I have 4 DMA channels. If I try to do 5 DMAs in parallel, I can't do it because I only have 4 channels. Right? And more importantly, once I do that, if my next time I want to optimize it and I only have 2 channels, well, then I say, oh, now we only have 2 channels, and so I can only do 2 in parallel. Right? So when we go and generate the implementation of these things, we take that into account. Right? So if you say, give me as many DMAs in parallel as I can get, it's a separate statement. This is how many you get, and we look at that and say, okay, we'll generate that for you. Okay? So all of this is built into the model. And when you start defining, okay, I want to do a simple loopback test, you say, these are the behaviors I want, this is the order I want them in, and it goes and figures out how to do that. Right? So we get a set of sequences that can run on your existing UVM environment, as I said. Now, when we move up a little bit, so now we're going to add DMA to this thing as well, right? So this is our DMA setup. So we have some interconnect here. We got our DMA and our RAM. We still have an AHB agent up here. This is the thing that's pretending to be the CPU. It says, okay, I'm going to set up a DMA transfer. So I'm going to load the data. I'm going to transfer it. Right? So I have this data buffer here. After I load it, I'm going to transfer it from here to here, and then I'm going to check the data. So this is my buffer. DMA exfer can't happen until I've loaded the data, and I can't check the data until I've done the DMA exfer. I can do a number of transfers in between there if I want. So if all I say is I want to do a load, a DMA transfer, and a check, then there can be lots of other things that happen in the middle there. Right? I may want to add in the ability to say, okay, when I do this data here, so my source of one is the destination of the other, that's going to set that up. I can say for my data buffer, the size has to be somewhere between 16 and 128. And I can also have constraints on the action here. So the source and destination are going to be the same size, and the source size is going to be less than 64. I take all of those together, and I say, okay, when I'm going to do these things, I figure out that the data that goes out of this one has to go into this one. It has to be less than 64, but my size can be anywhere from 16 to 128, so I lay that on. So now my size is anywhere from 16 to 64. Right? So I put all those together, figure out what is legal to do, and then I go do it. Right? So the constraints are composable, and all relevant constraints get applied across the system. When I go and put this together now, I have my UART here, so I'm going to do a DMA transfer and check the data. So in order to do that DMA transfer, I got to get the data from somewhere. Well, it can come through a series of DMAs, but eventually I got to get down to a load. So I have to know where I am at the beginning. I may actually just do the load here and transfer it from there. Right? Either one of these is valid. And I might also do it and eventually get the data from the UART in the first place. Important thing to notice here. All I said was I want to do a DMA transfer and check the data. That's all I said. When I go and figure this out, right, I can do that in UVM pretty easily. But if I want to account for all of these things, I have to start at the beginning. And in my UVM sequence, say, do this, maybe do some of these, then do this, do this, do this, right? I have to start at the beginning. Here, I started here. Right? Everything that happens before that gets inferred by the system because of the rules. I don't have to go back and write all of that. I've already given the rules for how to figure that out. Okay? So a portable stimulus model can actually look back in time, if you will, and figure out what has to happen in order to make the thing that I really care about legal. And that's really the value of portable stimulus. Okay? Because when you start figuring all of these things out, right, why do we do constrained random in the first place? Okay? Used to be a long time ago, I worked with a guy whose job it was to do QA. And he was really good at looking at a design and saying, you know what? I bet the designer didn't think of this. And he would write a test that would do that, and it would break, and then the designer would have to go and fix it. Okay? There's only one of him. His name is Jerry Ventura. If you know him or knew him, he's a great guy. Tell him I said hi. But he's not around anymore, at least not that I've seen lately. He's like, right? So we need a way of doing that automatically and doing it for in a lot of cases. So that's where constrained random came in UVM, right? The ability to randomize the contents of a transaction gives you a slightly different sequence and can uncover some bugs. This takes that to the next level. It's not just what are the transactions that are happening, but it's what do I need to have happen to get me to here. And when these things start happening in lots of different orders, as long as they're all still legal, this is where the bugs are going to come in. Okay, and we actually just had a customer do this, right? In very short order, they took this. They had a really big piece of highly configurable IP, and they had 300 UVM tests that they were running. And with one portable stimulus test, they were able to, first of all, match the functional coverage that they got, but also uncover a bug that they did not find with UVM because of the ability to do this. Okay, so that's really important. So when you go back to your boss and say, hey, we really got to do portable stimulus, he says, why? You say, because first of all, it's easier. I'll save 50%, as Adnan said, in creating the test in the first place, and it's going to uncover bugs that I wouldn't be able to find with 300 UVM tests. And by the way, each of these things can also be composable, right? So a given action can actually have a lot of sub-actions underneath it as well. Okay? So if I then move up and say this thing that was a UVM agent is now actually an embedded processor running C code, I can run the exact same scenario in this situation because the behavior is irrelevant to the abstract model. The abstract model is the same. The schedule is the same. All we have to say is now instead of doing UVM to make this happen, it's C code. And everything else is exactly the same. So how do we do that? How do we say this is the target implementation, right? So we have different targets. An atomic action, the lowest level thing, is what gets turned into an implementation. Right? So you'll hear this term, atomic actions. We call these things exec blocks. This is what defines for an action what the implementation is. And then we have a generator that assembles that target code according to the schedule we define in our activity in our abstract model. So there's several ways that we can do that. The first and the easiest way, the 1.0 way, if you will, is what we call target template exec blocks. So we define a one-to-one mapping. Basically, it's target code with some holes in there for values that got generated by the test generator, right? So for system Verilog or C, you had to write that code and leave these little holes. And we use double braces. We call it mustache notation, right, to put the values in. So when we go and generate it, we just take that template, fill in the values, and put those all together. And that's how we generate the code. So it requires a separate exec block for each target language, but it's really easy to manage that in PSS through packages, inheritance, extension, right? So you basically say, okay, first I want to use the system Verilog package to implement these things, and then I wanted to use the C code implementation for these things, right? So you basically have the abstract model, the exec blocks get pulled in through a package to tell which exec block you want, and it has the target template in it. Then we added in, I think this was 2.0, right, was the ability to do procedural interface, right, basically import functions. So you say, okay, I have this procedural interface. I'm going to call a function with a number of arguments. And so from that, I then have to supply the implementation of that function in either system Verilog or C. So the portable stimulus model doesn't change. It's just calling this imported function. But I still have to implement the function in both system Verilog and C. And this can be fairly involved, right? But if it's a big case statement or, whatever, state machines, something, we know how to do that in both system Verilog and C. We just have to do it. Okay, but the portable stimulus model, there's only one. So it's easier on the portable stimulus side. So this lets you have one exec block per action type, and it simplifies your code management in portable stimulus. You don't have to worry about saying which package you're going to import or whatever. Right? Then in 2.1, what we added was this idea of procedural control constructs. So in my exec block, I can actually define the algorithm as part of my portable stimulus model at an abstract layer. And so each of these things is going to call a relatively simpler implementation for either system Verilog or C. Right? So the complex control flow is up in the portable stimulus model, and all I got to do is say each of those nodes is supplied by system Verilog or C. So all of the hard work is done in the portable stimulus model, and it's much easier to deal with this now, and improves the portability as well because you simplified the migration between languages because you don't even have to re-implement the hard stuff. All you have to do is say, okay, this is a register read. This is how we do it in system Verilog. This is how we do it in C, or register write, or whatever. So now in 2.1, we've enabled you to do most of the hard work up in the portable stimulus model, and it makes it much easier now to reuse from one place to another. So we have a PSS model, and now for those of you that have been here in the past for these portable stimulus tutorials, this diagram is going to look very similar to what you've seen in the past, but there's one really big difference. There's only one of these. It's a portable stimulus model in PSS. There's no C++ anymore. So we get the scenario model for that, and once we compile it, we solve that. We solve all the constraints. We figure out what the rules are. Right? So we now have this big thing that's the solved model that we call it, and then we go and generate the test for that. And that test can be a set of UVM sequences that are going to run in your UVM test bench, or as we mentioned, it can be a combination of UVM and C that are synced together to implement the exact same thing on a very similar test bench. Right? If the UART VIP is the same, you're going to do the same UVM implementation for that, but you might have a different implementation for the C stuff on the processor level. And by the way, this kind of thing, the solving and the constraint, the test generator can be done at either gen time or runtime. Right? There's nothing in the spec that says one way or the other. It doesn't say which one's better or worse. It just says you can do it either way because ultimately you don't care. So what happens is we define these actions according to a schedule, and each one has an exec block. And then we supply the implementation of those. And if we say I'm going to go to system Verilog, we're going to generate the system Verilog implementation of all of these actions and bring the schedule over. So we do all those little pieces of system Verilog according to the schedule. Right? In parallel, it's a fork join, right? Whatever we need to have happen. Or if we generate C code for that, it's the exact same schedule. Right? So we need to know what your threading package is to say these two things are going to run in parallel in C or whatever, right? Your RTOS, however you're going to do that. And if you want to mix them together, we can do that too. So that's how portable stimulus works. Those are some of the important concepts. Notice, no code. I did it. All right. So now I'm going to hand it off to Matthew, who is probably going to show you some code. So Matthew from AMD. Any questions about that for now? Yes. How does functional coverage fit into all of that? Okay, what do you mean by functional coverage? No, okay, two answers. So the first is what we think of as functional coverage in UVM, cover groups, etc. That's actually built into portable stimulus. We refer to that as data coverage. Okay, so you can keep track of, what were the values of the sizes of your DMA transfer or whatever, those kinds of things, right? In 3.0, and I'll talk a little bit about it later, we're actually adding in what we're calling behavioral coverage. Right? So the ability to say, okay, when I went and inferred all those things, did I happen to get two DMA transfers on different channels that overlapped each other? That kind of thing. So we added that in 3.0, and we'll talk about that a little bit later. Okay? Anybody else? Yeah.
So you mentioned the constraints are solved outside the UVM sequences, right? It's solved in the PSS model.
Yeah, constraints are solved in the PSS model outside of UVM, yes.
Does it mean that your sequences that are generated are never going to have the RAN with the constraints, like the system?
Okay, does that mean the sequences that are generated are not going to have the system Verilog randomization call? Yes. Okay. Most likely, actually. Okay. What is most likely going to happen, if you think about it, okay, when I go and if I have this graph of things that can be generated, okay, if I'm going to randomly walk through that graph, right, any particular path I take through that graph is a directed test. Okay. So when I do that, okay, what I'm going to do for that is for each of those steps, I may actually wind up calling a sequence in UVM to say, do a transaction at this agent. Okay? That low-level sequence will still generate the transaction object according to values that were set from the top. Okay? The thing that will generate out of portable stimulus is usually going to be a UVM virtual sequence that's going to say, do this sequence at the same time I do this sequence, right? And do it over here. Okay, so at the agent level, you're still going to randomize the transaction that gets generated. But the values that are used for the constraints or whatever are going to be defined a priori by the solver in PSS to make sure that what you wind up doing at the agent is legal in terms of the overall scenario. Okay? Does that make sense? Did I answer your question?
Yes.
Okay.
Just another
Yeah.
comment. So because in VCS we have this ICO and all that, which is working at the constraint solver level, right? So those kind of things probably cannot be much.
I don't know what that is in VCS, so I can't answer that question. So, okay. Yeah. Yep. You know what? I'm going to go around with the mic here.
No, it's just a question in relation to the PSS model
Yeah,
itself.
keep it closer.
So to the PSS model itself. So when you describe the actual the algorithm, so as you were going higher and higher in the PSS model,
Yeah.
very difficult for the RTL verification engineer to understand, the system level. If you think
Yeah.
of it, we're very very good at the low level, but very hard to understand the system level.
Yeah.
And I guess that's where the software architect would come in. Can you talk a little bit about the person or the people who would actually work at that level to actually to define the sequences that you're effectively trying to create through the PSS model? Who would do it?
Yeah, okay, good question. Who would do that? Any of you guys want to take that one? Yeah.
I think it's a really good question. I think the IP level models that how to make an IP do something, that comes from the UVM engineer, but how those IP models plug together comes from a system integration engineer, and then eventually those things do get used by the people, by the architects to define what are the production use models we expect to see. So PSS gives you a common flow, right? A common representation that multiple stakeholders can add to.
Prabhat, you want to add to that?
Yeah, hi. In my ideal world, actually, I've been thinking about this a lot. The very high-level abstract sequences, be it an IP level or whole SoC, should probably come from architects and firmware engineers. And they know a lot about it. We have been telling that IP team knows a lot about the real IP, but the actual use cases are known by architects and firmware team. And the language is concise enough that you can create very high-level, say, power sequencing of my IP or security sequencing, very high-level state machines and whatever by architects. And same goes for IP level. Architects can create those high-level model. They will have to do more work, learn a new language, and not write Word documents. But in my ideal world, that's the best place to start.
Right. But the nice thing about it is the stuff that they have to learn about PSS really isn't that much. They don't need to know all of PSS. They need to understand the abstract model to be able to do that. Right? So the learning curve there isn't as high as you might think. And the value is going to be you basically have an executable spec, right? That's the thing we've been talking about for 20 years. This is it, right? Anybody else? Yeah.
Yeah, so you talked about, you define these rules of how things are supposed to work. But like you mentioned your friend, the reason he was so good is he broke the rules. So how do you, does this...
No, he didn't.
Okay,
he didn't break the rules.
But you have
he exploited the rules by coming up with scenarios that the designer didn't think about.
But we do have to try scenarios that are going to be illegal. We got to try error injection.
Yeah.
So how do you link that to the pass-fail? Because in those cases, it's not a fail if you're actually injecting errors.
Yep. Right.
You get what I'm saying?
Yeah. So the nice thing about portable stimulus is, and this is the first time I'm ever going to say this in public, everybody, okay? This is it. Aspect-oriented programming isn't always bad. Okay? So we have not only object-oriented inheritance, extension, derivation of one object to another type, but we also have extension. So it's very easy in portable stimulus to add in a different constraint to say, okay, I've been designing as if the maximum packet size is going to be 64. Let me now say, okay, actually you can go up to 128. Can I handle it? Right? So you can actually very easily layer on additional constraints that way. And you do it kind of from the outside. Think about trying to do this in UVM, right? If I have this really extensive set of UVM sequences and stuff, how do I reach down in there and set a constraint like that? Portable stimulus lets you do that very easily. Okay? So that's how it works. Anybody else? Yeah.
Hey, so you mentioned these items in PSS. Are those the exact same ones that are used in UVM, or is there any correlation between the two, or how do those work?
The item, you mean like the flow objects? Buffers and streams, yeah. So those are not always the same thing, okay? Right? A transaction in UVM is whatever you need it to be when you go and communicate with the DUT. Okay? The object that gets generated that we use in portable stimulus will typically have values that are used when you go and generate the transaction. Okay? So it's very rare, I think, and Matthew and I actually had a paper a few years ago about this in portable stimulus, right? You don't typically model the data in portable stimulus. You can model constraints about the data. How big is it? Maybe some tag information or something, right? But that's not the data that you use. When you go to UVM, you'll use that information when you go and generate the data that gets sent out. Okay, that kind of thing. So the important thing in portable stimulus is really more the scheduling implications of those objects, right? This thing has to generate the buffer before somebody else can use it, right? Or this is a stream. These two things have to happen in parallel to be able to share that stream. And the parameters that get passed back and forth through the constraints of both objects and the object itself, both actions and the object itself, define that relationship. Okay? Anybody else? Yeah.
So
all right, we got another few minutes for questions here, and then we'll take them more at the end.
So just following up for his question, right? So in UVM for drivers and monitors, you have these sequence items that you really need for us to drive, right?
Yeah.
So when you will be having a portable stimulus, how do you, let's say we have an existing test bench, right? And we want to remove all the sequences and have the PSS model come in.
Okay, I never said remove all the sequences.
Sure, I mean, we have the PSS model come in. So how do we kind of relate to those? How much change would be required in each of these individual components to kind of get that in?
Pick one sequence that you're thinking of, okay? What does it do?
I mean, it would have a sequence item, and then the
what does that sequence item do?
It just translates gives the data.
What's the behavior that you're trying to accomplish with that sequence?
I'm not getting you.
Why are you executing that sequence? What's it going to do? What's it going to make the design do?
I mean, it could either pump in data, it could have control signals, it could have data.
Exactly.
Yeah.
So at the PSS level, this is going to pump data into my thing.
Mm-hmm.
Okay, that's the action.
Okay.
The implementation is going to be cause the sequence that I already have to execute and do that.
Okay.
But from the PSS perspective, all I care about is it's an action that's going to pump data in.
Mm-hmm.
Okay. So when I go to C code, I'm now going to have C code that's going to do the same thing that my UVM sequence did.
Okay.
What I'm going to define in my portable stimulus model is the parameters that sequence is going to use to to pump the data in according to the constraints I set in my scenario in my PSS model.
Okay.
Okay?
But how does that answer the question that we would have to still change all the component code to kind of be a backward compatible with the PSS generated output? So PSS would be throwing an output, right?
What you're going to generate out of your PSS is going to be a UVM sequence that's going to say, do this UVM sequence that you have with these parameters.
Correct, but eventually it would boil down to the sequence items that the sequence is going to be giving to the drivers, right?
Yeah.
So how would you you would still need to probably change the drivers to kind of match, hey, this was what I had done earlier, no? Okay.
Because in your current UVM test, right, you have some virtual sequence that says, okay, go execute my pump data in sequence.
Okay.
That virtual sequence is now going to be generated by PSS.
Oh, okay. Now I understand. Okay, makes sense. Yeah, thanks.
All right, great. Okay, last question before we move on. Oh, all the way in the back, sure.
Of course.
All right, last question. Make it good.
Okay, so it mentioned that this would generate basically like virtual sequence,
yep.
right? For and my question is, would this be something that you run and it produces a new output every single time, or with the portable stimulus model, generate the same output each time that you ran it based on your defined rules, or does it have some random?
Okay.
In that sense.
Sure. So that's a tool issue. But what we have said is that the models are determinative, right? So most tools, and I can think of one in particular that I can talk about, if you run the solver with the same seed, you'll get the same solution, the same scenario, right? Now, that scenario may, as we mentioned, use the UVM randomization, right, of the actual transactions. So there's your usual simulator seed that gets used for that as well. Okay, so you basically have two seeds now that you have to manage. But if you want to recreate the exact same thing, you run the PSS solver with the same seed and tell the simulator to use the same seed when it randomizes your transactions. Right? So in the same way that UVM can replicate a scenario with the same simulation seed, if you will, portable stimulus will generate the same solution of your PSS model with the same seed. Right? And if you run it with a different seed, you'll get a different scenario. Okay? All right. We'll now hand it off to Matthew.
All right. As Tom said, I'm Matthew Balance. I work at AMD working in a methodology team developing DV methodologies and actually working quite closely with PSS. Now, Tom was very successful in showing no code in his section, so I'm going to double up and show twice as much just to compensate. But really, okay, so we started at a high level talking about motivations and some of the key features of PSS. Now is when the rubber kind of hits the road. Let's see how we can use PSS, apply it at the block level, where there's quite a bit of test realization, quite a bit of detail code, and then moving up to subsystem SoC post-silicon. Prabhat and Sergey will talk about that, where there's a lot less detail in terms of how we access our designs. All right, so our goal starting at the block level is really, we're going to focus a little bit on our customer and a little bit less on ourselves at the moment. Our goal really is to create reusable content for the upper level integration teams to use, for the SoC teams, for the post-silicon teams, and we're going to create test content that gets our IP initialized up in a running mode and exercises some key operations. Now, obviously, much of the time our consumer team will actually request that we confirm that we've verified certain things, and we'll touch on how we can do that with PSS. And obviously, those consumer teams themselves may be using UVM and or embedded C tests, and our test content will need to work in both of those environments. Now, that's not to say that the test content we produce is only useful to those teams. PSS is actually very useful, used in a UVM environment for block level verification. We get the ability to create much more complex scenarios much more easily, and the UML diagram basis of PSS actually provides a really nice medium to discuss test scenarios with other teams. It provides a nice medium vehicle there with teams that are really span a variety of disciplines. Now, Tom talked about kind of the two aspects of a PSS model, the model itself and the realization. And at block level, we really care about both of these aspects quite a bit. As we move up, we care more and more about model and less about realization. And that abstraction is important. But at block level, we have to really think about both. As Adnan said, it's the block level guys that know everything about an IP, inside and out, the registers, as well as all of the kind of the ins and outs and operation modes. So we'll really focus on this aspect at block level as we're creating our test content. Now, there were just some discussions about sort of how we hook up PSS to a model. What sequences can we reuse? And one thing to realize is there actually exists a very common interface that almost every one of our IPs, I would say 100% of our IPs have, and it's the register interface, and it's the memory interfaces. Even if you're dealing with a serial communication device, much of the way you interact with that device is via memory map registers. And this actually provides a really nice I'll call it a universal interface from PSS into nearly any IP. Now, in pretty much any environment, we will not just use direct, address, accesses to address our registers. Almost every environment that we have provides some sort of register access layer, and PSS is no different. The goal is to go from code that looks kind of like this, where we're programming a register with a bunch of shifts and manipulations, and good luck figuring out what that means when you come back to it 6 months from now, maybe even tomorrow. And have something that looks a little bit more like this, where you have names for fields, you have you can understand a little bit more what's going on here in terms of, in this case, we're programming a control register for a UART. The details don't really matter. It's to abstract up a little bit without, of course, sacrificing any efficiency. And we have register access layers defined for most methodologies. If you're a C and C++ guy, there's a mechanism for doing this. UVM has its register model. PSS also defines a register access layer to let you do this same type of abstraction. Much of the time, these register descriptions come from some higher level description, system RDL, IP exact. You're often specifying these things way up front, very early on. So I'm going to talk a little bit about the mechanics of the PSS RAL. But keep in mind that last bullet. Most of the time, you're not going to be creating this by hand. You'll have some automation tool that does this for you. But having this defined as part of the standard is actually very important because it enables tools to do that automation step. It enables creation of very efficient descriptions that are easy to read. So in 2.0, we brought in a definition of a PSS RAL. It's really focused on efficiency. It's focused on enabling, abstracting up from the details of accessing registers. Fundamentally, what we do, we use kind of similar to what you would do in C. We define packed structs as a way to lay out the registers themselves and give widths and names to the registers. We can build up blocks of registers built in terms of those lower level field layouts. And then there are a series of access methods that we can use to access the registers. We can read and write the registers in terms of the packed structs, and so you deal with the mnemonics of the register fields. We have access methods for dealing directly in terms of the kind of the integer image of the register content. And in 2.1, we actually added some efficiency methods to do a very common operation on registers, which is to read the current value, update a couple of fields, and write back the new value. So we added sort of these read, modify, write convenience methods that really kind of makes the code a lot more compact. Rather than reading, modifying, and writing back, you simply have a single call that does all three of those operations. Now, again, as I mentioned, despite the fact that I showed code there, showed how you could set up these registers manually, in almost every case, you'll never do that by hand. Every company has some register automation tool that takes in a variety of formats, whether that's IP exact, system RDL, custom, whatever, and spits out a variety of output formats, whether that's the register implementation, whether that's the UVM RAL, or it could be the PSS RAL. So most of the time, this is exactly the flow that you'll do. You'll take the high-level description, you'll get out the PSS RAL, and then you can deal with accessing registers at a more abstract, higher level. So just to prefetch that a little bit as we walk into alternating a little bit between modeling our IP-level features and then how those connect to test realization. So let's come back to the modeling layer. Adnan talked about how we set up some of these relationships and requirements on actions. And those that contract, that set of required relationships, is actually very important as we move up in integration level because it ensures that we don't make mistakes in connecting together our test content. So let's start with an example. One of the first things, and I think Tom might have touched on this, one of the first things we have to do before we use an IP is initialize it. Most of the time, if you don't correctly initialize the registers, you can program it all you like, and it's just going to sit there and do nothing. Or maybe something bad. Who knows? So if you get a piece of test code from somebody, and it's supposed to perform some operation, if it's C code, there's nothing about that C code that tells you you need to initialize the device. You have to know that. You have to talk to the guy that wrote it and say, what initialization should I use here? PSS gives you a way to annotate that requirement on your action. And the common way to do this for initialization is with a state object. So what we're going to do is start by defining a initialization action for our UART. And this will output a state object that captures the configured state of the UART. It has all the standard things like number of bits, whether your stop bit's enabled, baud rate, so on and so forth. And as we're putting together our test content, we'll want to create a few different variants of this type of initialization action. We'll want to create one that's kind of fully random, can be configured anyway, and then we'll want to create a few sort of sanity cases, typical bring-up cases. So when we think about connecting this to test realization, we have kind of a parallel. Okay, here's our register view of our UART, and this was created, of course, by our RAL automation tool. Defines layouts of the registers in the field, specifies the registers in the UART. Now, we're going to come back and set up a programming sequence to take the configuration, the state of the UART that we are setting up, and actually connect that to the realization, program the UART registers. And as you can see here, this is pretty straightforward. It's pretty readable because we're abstracting up. We're using mnemonics for the fields of the registers. We're writing in the bits, the stop, parity, so on and so forth. We're doing the calculations for the baud rate and programming those in the divisor registers. So again, this is capturing the IP guy's knowledge of how to set up the UART, the calculations you have to do based on this higher level description of the mode in which you want the UART to operate. Now, as I mentioned, it's very common to provide sort of a little family of specialized actions. So we might want to provide sort of a kind of a sanity setting. UART will always work in this mode. Really no variability here. Everything's locked down. We might want to provide some specializations along certain axes. So that's no parity, 8 bits, one stop bit. That's very common. But the baud rate varies. You can change that. So if we provide these, our end consumer has a variety of very simple ways to get the UART into an operational state. But again, one of the points here is that we can start to condition our behavioral code on the UART being initialized. So if you notice here, our transmit data action here takes in a UART state object. And so what this is saying is, I need to have had somebody initialize the UART before I can run. And I can actually put a constraint here and say, this has to have happened. So this is really helpful because if I give somebody my UART TX action and they attempt to just run it on its own, the PSS tool is going to say, hey, wait a minute. You didn't initialize that. This is not going to work. Now, the PSS tool might randomly infer an action, any initialization. The PSS tool, it'll infer an action, and the user might say, well, okay, I actually wanted it initialized a little bit differently and pick a specific action. But one way or the other, you have a much better chance of getting things running out of the box with this test content than if somebody just handed you a piece of C code. One thing that PSS does, and we're definitely into code here, because PSS is an object-oriented language, we can factor out some of the commonalities. So we might have a dozen different actions for the UART. We can kind of refactor things and say that all of the behavior actions depend on the UART being initialized. And that's a way to sort of keep our code a little cleaner. Very standard OOP approach here. We can also get a little bit more involved in our requirements here. So we can place some requirements. Not only do we need the UART initialized, but we need it initialized in a specific way. So, let's say we have an action for sending huge packets on the UART. We know that these are going to take forever to run if we haven't initialized this in some higher baud rate. And so we actually just place the constraint here to say, in order to run this, this bulk action, you really need to have initialized the UART in a fast baud rate. So this is a way to sort of place a little more nuanced requirements on between your test content and the rest of the scenario. All right. So as I mentioned, in addition to sort of providing that initialization content and some operation content, one of our deliverables to the SoC team is some coverage information showing that we validated certain modes of operation as part of our verification work. Fortunately, PSS, as Tom was mentioning earlier, has both data coverage, which it's had since really the first release, and that's what we're showing here. So this is very symmetric to system Verilog coverage in terms of capturing the same types of constructs. So it aligns very nicely if you are sort of comparing this or capturing this in a coverage database intended for system Verilog coverage. So here we're capturing that we've verified all the baud rates, the different bit modes, crossing together some of those combinations as well. This is nice both in terms of capturing metrics that we'll share with our consumer team, but also because of the declarative nature of PSS, we can actually grade our coverage before we run the tests. Once we generate those tests, we can basically collect the coverage that will be achieved by running them and have a much better sense of whether we'll hit all the combinations we care about before we even run a simulation. Okay, so we've talked a little bit now about capturing our initialization content and how, at least at a high level, we would condition our behavior on that initialization. So let's move on and talk a little bit more about, a little more depth about the behavior aspect. So we'll switch and talk a little bit about DMA. You might recognize the diagram from earlier in the presentation. So let's again kind of revisit our DMA operation. And specifically, let's think about sort of the requirements and the required relationships that need to hold in order for us to do this memory-to-memory transfer. So obviously, kind of the first obvious thing, we've been hitting on it, we have to initialize the DMA before we can run this. That's easy. Now, we also need to have a block of source data to transfer. And this really needs to be initialized because transferring uninitialized data, okay, we don't really care about that. So this needs to be provided to us. We need access to a DMA channel. We need dedicated access because if multiple behaviors all try to use the same registers, same channel at the same time, that's not going to end well. And then finally, as a postcondition, this action, this behavior produces a block of memory that can be used by others. And that's available only once the behavior is completed. So let's see how we do this in PSS. We capture this contract for the action as follows. So we've been talking about the input state for initialization. We capture that as an input to our action. The DMA must be initialized. We have a lock statement that says, okay, we need dedicated access to a DMA channel. And we get some information about the specifics of that channel by locking it, by claiming access to it. We have an input buffer that we require to be produced, available before we can run. And this will hold a pointer to our input data. And we have an output buffer. This will be the output data that exists after our action is complete. And then we have a couple of constraints here just to kind of enforce sensible relationships. Our DMA is going to transfer the same number of bytes to the output that it received on the input. And by the way, we of course need our, we need to have initialized the DMA. Now, another aspect of the contract that we're capturing with our action is around memory allocation, memory claims on the system. So at this level, generally at an IP level, our claim information is fairly simple. We keep things fairly, there's not a lot of nuance here much of the time. And so you see up here there's there's an address claim field right here, and we're basically placing a constraint here to say how much memory we need, and that depends on the size of the buffer. And once we have claimed that memory, PSS has some methods for getting handles to the claimed block. Think of that like a pointer that you can use with the convenience methods. And we'll use this in our test realization when we read and write memory. So let's take a look at how we connect this high-level description of a DMA action where we have sort of captured our key requirements. Let's see how we connect this back to the register fields. So remember that we claimed a channel, and inside that channel there's a field that says which channel we're talking about. And we're going to use that instance ID to get a handle to the correct instance of registers that we want to program. And then we can simply start programming those registers based on the selections that have been randomly made by the PSS tool. So we can remember that memory handle that we just created in PostSolve. We can get the address value of that and program that into the source register. We can get the value of the destination memory and program that into the destination register. We can get the size and write that into the size field. And finally, we go set the enable bit to get everything rolling. And then we have a little loop down here at the end. This is showing some of the little slightly richer code that we can write to deal with handshaking with the DMA. Loop until the DMA says it is done with the transfer. So a couple of things to realize. Again, this is pretty simple code to write. This is code that's kind of on par, I would say, with system Verilog code that uses the UVM RAL or C code that uses a RAL. So it's pretty straightforward for an IP guy to write, and they'll be doing this anyway in UVM. So doing the same in PSS, especially if you have the PSS model accessing the registers via your UVM environment, is pretty straightforward here. All right, so that was an easy behavior. But oftentimes our IPs have very complex behavior, and we want to simplify the integration, the subsystem and SoC guy's life. So we can use the encapsulation features of PSS to do this, to build up actions that are more complex. And because we have captured all the rules and relationships that must hold within this action, we can give a much easier to use API to the SoC guys to make use of that more complex behavior. So let's take a look at a case where we might do this with the DMA. So again, the goal here is, as IP guys, we're going to build up a more complex action that somebody can use without really understanding the details. That's the whole goal, frankly, of PSS. Let's capture our IP-specific knowledge, package it in a way that others can make use of it without knowing all of the low-level details. And they can do that safely. Now, I'm going to show a bunch of code in this section. Think of this not so much as, oh my goodness, that's complex. Come back to it at the end and think, okay, if I were provided kind of this API as an SoC guy, isn't it great that all of that complexity hides down in there and I don't have to worry about it? Okay, so let's think about our DMA engine. DMA engine's bunch of different accelerators do transfers via some form of in-memory descriptor chain. The idea is you've got this descriptor, it sets up a certain transfer, and then it maybe links back to a previous descriptor until you get to the end where there's some end of chain pointer or bit. Now, there's some set of rules that have to hold across this descriptor chain. First off, the memory for the descriptor chain itself needs to be valid for the duration of the transfer. We can't start yanking descriptors until the hardware is complete. All the source data that's going to be operated on needs to be valid before we start the transfer, because we can't predict when the hardware is going to get around to actually looking at the source data. And for the same reason, we can't start looking at the output data, the destination data, until the entire chain is completed, because we don't know until we get to the really end whether that is valid or not. And so we want to set up an action that sort of enforces all of these rules, helps us set up a descriptor chain such that the SoC guy just has to say, how long do I want that to be? They can go do their transfer, and they don't have to worry about any of the details of the linked list or anything else. So it's going to capture the things, the lifetime requirements. It's going to capture all the programming sequences. All the SoC guy has to do is run this action, maybe constrain the length a little bit to get something sensible. All right, so how does this work in practice? So we're going to have a couple of actions that are going to manipulate the descriptor list. One thing we might do is have an action that represents creating the end of the list. This is the initial action. And then we're going to have an action that adds any entry into the descriptor list. So it adds an entry. And with these two actions, we can build a descriptor list of any length. Now, as I mentioned, we need to make sure that the memory that we claim for the descriptors is held until the end of the transfer. And we're going to do this by sort of having a buffer that we use for some bookkeeping that's going to keep track of the descriptors that the memory that we acquire for the descriptors. All right. So basically what's going to happen when we run this, do a linked list transfer, we're going to have an initial action that creates the head of the chain, and then some number of add actions that add additional entries into the chain. And then at the end, we'll have a kind of a finish up action that kicks off the transfer and waits for the DMA engine to signal that it's done. Now, so remember, we need some bookkeeping place to put the information about where the data is. So we need to keep track of the memory blocks that we have allocated for the descriptor chain. We also need to keep track of what the last descriptor pointer is. Because every time we add a new descriptor, we need to put a little pointer in to say, okay, what was the last descriptor? And we're going to manage this information in a PSS buffer object that we use when we're setting up this chain of descriptors. So specifically, we have an address handle, which is representing the handle to the last descriptor. And we have a list of address handles, which is accumulating all of the descriptor addresses that we have allocated. The reason for us to have this list here is as long as we hold on to the descriptors, or as long as we hold on to the address handles, PSS knows that we're still using them. And it's not going to free them in the middle. So this is our way of saying, hey, these are still busy. We're still using them. Don't get rid of them. Don't let anybody else use that memory just yet. And then again, we have our next descriptor here, which allows us to, in our programming sequence, program the pointer between our descriptor and the last one in the chain. All right, so our action for adding a descriptor to the chain looks like this. We have our chain buffer that we're using to build up the chain. We have source and destination data. We have a claim for the descriptor that we're about to set up. And of course, we have some constraints to make sure that we allocate the right size of memory for that descriptor. Now, again, we notice our post-solve here. Once all the solving has been done, we're going to do a little bit of bookkeeping. We're going to get a handle to the descriptor memory. We're going to update the next pointer in the buffer that's going out, and we're going to push the descriptor into the list that we're using to make sure that we manage the lifetime of the memory. Again, there's a little bit of code here. It's a basic linked list building code. We're doing next, last type of pointer references, and we're managing the lifetime by hanging on to memory blocks in a list. Now, this is where we get a little bit different in terms of test realization. We've talked about using registers as a way to program memory, but this, of course, is in-memory data structures that we have to program. Fortunately, PSS provides a good way to do this as well. We can model the memory layout of descriptors using packed structs in PSS as well. So here we have the layout of a control status register that's within the descriptor, and down here we have a packed struct that lays out the CSR fields, source data, destination address, and the next pointer as well here. And we can lay out these in-memory descriptors, capture them in PSS. This also might be something you generate from a higher level description like systemrdl. And we have convenience methods in PSS for writing and reading this type of data. So it makes it really easy for us to fill up this type of information at the abstract level and then write it to memory using a single PSS function. All right, let's see how we do the test realization for adding an entry to our descriptor chain. So down here in the body, this is the test realization code that actually will run in your UVM test bench or as your C code. We're using our packed struct here, our descriptor. We're filling up the fields based on values that PSS has solved up here. So we're putting in the size, the source address, the destination address based on the handles that come in. We're doing a little checking here to see to set up the next pointer appropriately. So specifically here, if we get to the end of the chain, we need to set a special bit end of list in the CSR, and we need to program the next link to be null or 0 instead of having an actual address value. So this is just populating the packed struct. And then we can use the PSS convenience method, write struct, to actually perform a copy of this into memory. So slight variation on our test realization via registers, but it accomplishes the thing that we need to, which is updating target memory. Obviously, once we build up our chain, we'll want to run it. And this code is actually very similar to the code we already looked at in terms of getting a handle to the channel registers based on the instance that we're working with, writing the head of the descriptor chain into the right register, enabling the channel and putting it in kind of a descriptor chain mode, and then finally polling the DMA until it comes back and says, okay, transfer complete. So actually nothing terribly interesting or new there, but it's very similar, very easy to write code, again, on par with what you kind of already know how to write in UVM. Now, the final thing we want to do is sort of complete the task of creating that single action that we can hand off to the SoC guys where they can turn a knob and get a chain of descriptors without much thought. And this is all because we've captured all of the rules about how these lower level actions need to interact safely such that they get the right memory, they don't leak memory, they don't stomp on memory. So this is the high level action. What we're basically doing here, we have the beginning of the chain, we have a replicate statement, which think of this as sort of an unrolled repeat loop, where we can unroll some number of add descriptor elements to the chain based on the length that the user has constrained. And then at the end, we have our kind of run the chain action, which programs the registers, waits for the DMA to complete. So at the end of the day, what we can provide to our end user is this nice high-level action that has one little control knob and hides any complexities that we need to know about as IP people about all, how descriptors go together and all the requirements there. And so they can reuse this knowing not only that it works safely on its own, but that it will work safely with any other PSS content, and it won't stomp on that memory either. So this is a very nice abstraction capability to build in complex things and make them available to be very easily used. Okay, last couple of little wrap-up slides. Now that we've captured our initialization contents and behavior, we actually want to think about how we plug this into our UVM environment, because we'll want to be running these behaviors in our UVM environment. So thus far we've primarily talked about the actions, but we also want to sort of encapsulate those up into a PSS component, which is a structural element. So kind of the rule of thumb is for every IP block, every type of IP block, you'll have a component that wraps up the resources that block has inside of itself, things like DMA channels. It will have all the behavior actions inside of it. So this is kind of a unit that you deliver as representing the operations that can be performed by your IP. Now, in our environment, in our UVM environment, we'll want to think about how we connect this in. And so we'll be creating sort of a wrapper that is specific to our UVM environment that has an instance of our design and some other things that we need to interact with the UVM environment. Things like the register model instance itself, any specifics in terms of how we connect to the register adapter or agents within the UVM environment. And this is to keep our IP-specific code separate from our UVM-specific code. We've been talking about programming this IP in terms of registers and memory. And there are a variety of ways that you could make the connection between PSS and your UVM environment. Keep in mind that we've looked at kind of the user-side APIs for reading and writing memory and registers. There's sort of a parallel set of back-end APIs that PSS can access when reading, writing memory. And we can implement these read and write functions in terms of our UVM environment. One approach might be to implement the reads and writes directly in terms of the sequence items and sequences that run on your protocol agent. Another approach might be to directly connect those reads and writes up to your UVM register model and the register adapter, which is a slightly higher level, more protocol agnostic way of doing reads and writes. There's a variety of mechanisms here, but fundamentally you're implementing the read and write that PSS knows about in terms of your environment. Most of this is 6 lines of code or so. And so that's kind of it. So what we've done, we've captured test content to initialize our IPs. We've captured test content to exercise key behaviors and all of the relationships that need to hold when that test content is used. We've looked at how we use registers and memory to access, or the route to access memory and registers inside the IP. Basically, what we do here, or what we've done here, is to capture a lot of the rules that govern proper operation of our IP, such that the upper levels of integration don't need to worry about them in detail. The PSS tool can ensure that they're enforced and that they all hold. So in a sense, like Adnan was pointing to, we're capturing the IP guy's deep knowledge in a way that is kind of machine readable, can be enforced by the PSS tool, and somebody else doesn't have to worry about it in depth. So kind of my pitch is requirements capture and test realization is real portability, because you can then put these things together without dealing with the details.
My name is Sergey Haikin. I'm with Cadence, product engineer. My job responsibility is to make sure that this technology is actually deployable, scalable. I work with customers to make it tick and tape out chips. And actually, I would like to take this opportunity to thank to some early adopters who are actually sitting in this room. I won't point, but really huge thank you to all of you who took the risk over years, who believed in this technology and helped us to bring it to the prime time today, which we firmly believe that it's ready to much, much wider adoption in the industry. So I will be talking about subsystem and SoC-level testing with PSS. I would like to show some historical perspective first, because the way how we structured this tutorial was to start with IP-level applications. But really, in the beginning, it started with full chip level application, primarily embedded C, where similar to how Tom and Matthew were speaking about PSS driving virtual sequences in UVM, PSS was driving a library of software firmware APIs. So typically, when we introduce the PSS first time, we talk about those two levels or two vectors of reuse. One is horizontal across different platforms versus vertical across different integration levels. The people who were sitting here in the top right quadrant of this diagram have had way more challenges than UVM. Folks who were lucky, at least they had constraints, they had coverage, they had some element of reuse. Folks who are sitting here and trying to implement multi-core test cases in C had none of that. So they were in a world of hurt. And this is why that's where the first deployment of portable stimulus happened as early as 2018, when this portable stimulus technology emerged first. Having said that, PSS 2.1, which Accellera released about half a year ago, presents a set of new opportunities for SoC applications, in addition to all the opportunities for IP-level verifications that were already presented earlier. Some of them have to do with coreless environments. So before, we were primarily using PSS to drive activation of various firmware APIs. Today, we can use PSS to drive coreless environments, where we use bus functional models to represent cores before actual RTL implementation of cores is present. Shift left, of course, is now possible with features of RAL that Matthew described earlier. So now if we are operating when software is still not available, we can utilize this functionality to still create SoC-level test cases which drive the hardware using direct register accesses. And finally, virtualization, obviously a huge topic today in SoC design. So there are a few new features in PSS 2.1 which facilitate implementation of mechanism that has to do with address translation, system view of different memories, things like that. So I would like to start talking about what kind of bugs we're targeting with PSS at SoC level, and what are the typical examples of content that we're going to be creating. So first of all, we're trying to target bugs which are impossible to find at lower level environments, typically bugs that are hiding on the seam between hardware and firmware. Some of the aspects of desired behavior are not necessarily covered in specs. I cannot write a scoreboard, some sort of a data integrity checker which catch bugs that has to do with power consumptions or performance. And finally, some people were asking questions about system-level functional coverage metrics. So we like to talk about high-level abstract coverage metrics. This technology helps to actually define what those system-level coverage metrics are and what they represent. So later on, I'll talk a little bit about that. In terms of what kind of content we want to run. So once I have a whole bunch of IP-level test cases, the first thing that I want to do with those test cases when I'm assembling my SoC is to coalesce them or make them run together to create interesting stress on interconnect and test concurrency of my design. Interesting things about PSS, since we think about everything the design can do as actions, it becomes fairly easy to take a test case which is designed to check correctness, functional correctness, and instrument those kinds of test cases with actions which turn off and turn on timers. And by doing so, I can take a functional test case and make it a performance test case with fairly lower effort, and that's what people do. Another huge portion of SoC content has to do with power. So starting with basic directed random sequences for just taking different IP through their power cycle sequences. The next thing that we can do is now mix those power up, power down sequences with actual traffic. And that's what we consider the main archetype kind of system-level test cases. We can start asking questions. What happens if I send a snoop to CPU that just went to sleep? How my system would react to that? A ton of bugs are found when we basically mix traffic with power across the system. And finally, there are a few different patterns that we developed with customers over time, which use PSS to validate various aspects of system behavior, which we call kind of chassis of the SoC, things that has to do with interrupt controllers, chip frequencies switching, things like, all right, I have verified some sort of traffic behavior, but can it still work while I start changing the frequency of my bus to different values that this bus supports? So those are the different challenges that we're facing. I will describe them, and then the rest of the slides I'll try to address those different challenges in terms of PSS solution. So number one is it's difficult to facilitate portability across different execution platforms. And this term portability has a lot of different facets to different kinds of portability. So if I'm working in simulation environment, I want to do both coreless with bus functional models, or I want to take my environment and make it run on actual processor. Similarly, on fast platform emulation, I still want to do the coreless, but now this coreless is no longer driven by bus functional model. It's going to be driven by some sort of a transactor or accelerated VIP, and again, processor driven. Finally, when I take this to silicon, I want to run it in CDP, I want to run it silicon board, and even on tester equipment in high volume manufacturing environment, that is going to be also processor-driven, but I want to make sure that I have one stimulus model can execute seamlessly across those multiple different, maybe 6, 7 types of environments that we're using to validate our chips. Another challenge, I want to be able to quickly initialize required IP, so Matt already talked a little bit about it, and Prabhat will talk more. I want to generate both complex and valid. Just one of them is not enough. Cross-IP traffic patterns. Classical example, again, is having to do with a resource allocation. If I have that many DMA channels on my DMA controller, I better not schedule more concurrent transfer than I have channels. Memory allocation management, huge issue with concurrent processing. When I'm creating those parallel data traffic patterns, I want to make sure that none of them stomp on each other's feet as they use memory. So PSS provides a number of features which automate memory allocation management in a chip. Another huge challenge is what happens when I make change in my register map, in my MMIO region definitions. Essentially, this is a third vector of reuse. I was talking about vertical reuse and horizontal reuse across different platforms and integration levels. That is a third dimension where I have similar but a little bit different projects, and I want to, with the flip of a switch, very quickly transition from one project to another where it changes only in terms of memory maps and things like that. Another thing that we want to address is proving coverage of key concurrent behaviors. So that will have to do with the system-level coverage metric that I already noted. And finally, we want to make sure that our scenario space or our abstract model is unified across all testing environments. And one example is what happens if I have I began with a register-based programming, but now I want, now my firmware guys developed a set of firmware API drivers as C programs. I want to take that same test intent and replay it now on top of in driver-based environment as opposed to just register-based. So those are the challenges. There are many of them. I'll try to show how we address them with PSS throughout my presentation. Okay, so how we really take this vision and make it deployable and usable in production? And the answer to this question is by layering it into two main layers. So one layer on top, where the actual verification intent sits, it's a hierarchy of PSS models. So all of those models are written in PSS language. They're completely agnostic, or almost completely agnostic, of what is happening at the bottom, and that is what we call test realization layer, which sits on top of those multiple target execution environments that we're trying to port our stimulus across. And one of the beauties of PSS is it's fairly lightweight, it's very agile, and the approaches to model could be either start from the top and go to the bottom, or it can go from the bottom to top. Basically, we can start asking ourselves the question, okay, what are the drivers or what are the sequences available in test realization layer, and start building IP models. And the reality of it is people approach this modeling somewhere in between, and I'll show a little bit more details on this later. So, how we approach modeling SoC, and we decided to go top-to-bottom approach because this presentation primarily talks about SoC. So we really like, when we teach PSS, we really like this analogy of constructing games. PSS is really all about formally spanning test spaces. And if I think about game design, like for example chess, I start constructing my test space by defining what are the rules of the game, what are the participating entities, and what they can do. So with chess, I have this many different chess pieces, and they can do certain moves in certain situations, and that's where we begin our PSS model. And then PSS activities traverse those test spaces, or going back to this analogy of game design, those are specific plays within the game that basically translate into interesting use cases that my test plan captures. And those specific plays or scenarios typically map into those system-level with coverage goal because we want to be able to track our execution against the plan. So in terms of reality, in terms of how that translates into SoC modeling, the participating entities translate into structural entities which comprise our SoC. So typically it's going to be subsystem models, IP models. In PSS language terms, those are going to be PSS components. PSS component is the only thing that can do things in PSS. And then scenario building blocks and rules, we begin by capturing our basic power IP and initialization rules, some basic IP scenarios like typically those are going to be things like initialization, configuration, and traffic. And then we also will capture various cross-IP traffic scenarios where those IP interact together. Once we have finished defining those basic structural entities and scenario building blocks, we can proceed to the second step, which is, okay, now I open my test plan and I start creating different compositions of activities in this test plan into something meaningful that makes sense to verify and run on my target platform. In this case, in examples, not all examples, but some examples are things like system traffic concurrency, performance, power, and cache coherency. So perhaps the one thing that I want you to remember from this slide is the PSS modeling mindset is all about, number one, focusing on formally spanning test space of SoC. Then we use PSS activities to describe those use cases per test plan, and I'll show you a couple examples of how it's done. And then we always need to think coverage, and as we comprise those activities, which basically test the entire test plan, we also need to focus on a subset of this test plan, which is going to be our coverage goal. Coverage goals are always a subset of test plan. They're typically much smaller than the overall test space scenario. So this is the first example of how we schedule or coordinate multiple different test activities at SoC level. The idea is here that I, as a SoC test plan owner, I took two test cases that were provided to me by IP, and those test cases implemented in PSS. I don't have much detail yet about how exactly they're implemented, and very soon I'll talk about different levels of detail that can be captured in those IP level scenarios. But what's important is that we use this keyword schedule, which instructs the PSS solver to randomly schedule this activity as long as the rules of the model are respected. And by clicking a solve button, we require a PSS tool to basically build a PSS scenario which would put those two test cases, in this case it happened to be concurrent, as they are scheduled together. We have UART unit test running together with DMA unit test. It is possible to schedule them concurrently, but if for whatever reason there may be some contention in resources or not enough memory, those two scenarios would have been scheduled one after the other. It also so happens that some actions were inferred by the tool. I, as a SoC owner, road that I want to say, when I want to say TX together with RX and DMA, but it actually inferred additional actions because the UART needs to be initialized and configured and whatnot. I, as a SoC owner, don't care, but I rely on PSS tool and PSS model to make sure that the resultant scenario is going to be correct. And PSS model is responsible of making sure that it's going to be indeed correct. There is detail behind it. This single DMA transfer descriptor test case was already created by Matthew earlier, and this is how it's built. We start with some write data action, we continue with actual transfer, and we check it. But again, as a SoC owner, I may or may not care about those details. Similarly, UART TXRX test case also came from IP, but again, in the shoes of SoC test creator, I really care about the high level of description, and this level of description may be of different levels of detail. So now there's IP. What happens when we start integrating IP or building IP models? The mindset pretty much remains the same. We again focus, instead of focusing on IP level aspects, we focus now on spanning test spaces of each IP. And we again use IP activities to describe IP use cases per test plan. And again, coverage, we can capture also IP level coverage models of the same. So at IP level, we maybe think about different things, because at IP level, we want to specify IP connectivity, resource, all kinds of software contracts, all the things that Matthew talked about it earlier. And also IP is the first place where we typically start integrating with test realization layer. So that's where rubber hits the road in Tom's presentation. So that's where we have those, we start to define those exec blocks and maybe instantiate RAL if we're indeed using register programming. But this is optional step, maybe we're operating with drivers. So depending on which primitives, we call them target primitives, available in test realization layer, I may or may not do all of those things when I'm implementing the IP. But again, fact of the matter stays that at a high level, in terms of PSS description itself, the mindset of modeling in the IP or subsystem is very similar to what we're doing at the SoC level. And this line in the sand where SoC begins, where a subsystem starts, really depends on different companies, different projects. Some large IPs could be a subsystem. So let's talk about the level of details that we need to describe when we implement those PSS models of IPs. So the key point is that the IP level may vary in how detailed or abstract they are. We could begin with very simple IP models which only have atomic action and exec bodies. So in this case, we're showing that same single DMA transfer action that we were already describing many times. And the only thing that we're showing here is we're letting PSS tool know that, hey, there's going to be some function available on the target platform, so we're saying import function. And this function is going to implement all the low-level details of behavior of this action, which is doing our single DMA transfer. This could translate eventually to some system-level sequence. This could correspond to activation of a C firmware API. And when we use this IP-level model in our system-level scenario, that's the only action which was going to come out. That's the only thing that we're going to see. However, when time progresses and we move on, we can take exactly the same component and we can refine it. And now we say, hey, actually now it does not correspond to just one firmware API or sequence. It actually a whole bunch of things. Each of them now will have its own exec body, and maybe even if I will proceed further, each one of them will expand into more and more and more elaborate, more detailed sequence progression of events. Yeah, and of course now it has the notion of resources. So the more detailed we go, the more benefit, the more bang for the buck we get in terms of things that we can do with this model. But again, one thing that I want to take you out from this is that PSS doesn't require you to be very detailed or very abstract. It's a decision that you can make as you develop your models. And then the next question, which managers like to ask, of course, is, okay, who owns those PSS IP level models? And it's a choice which depends on how deeply we have progressed with adoption of this technology in a company. So typically, in the very initial adoption of PSS, we start with a so-called IP test vector. So we basically go with this little minimal representation of an IP functionality which has only atomic actions and exec bodies. So those test vectors typically are supplied in the form of precompiled binaries or even source C code, or sometimes precompiled UVM sequences, or test vectors that were already captured and can be reused. The advantage of this is that we can already, just using this basic simple IP level models, we can benefit a lot of PSS functionality in terms of scenario composition. So now I can take those basic atomic actions and glue them together into meaningful flow, sequential, parallel, things like that. And it's cheap because those test vectors are typically available, so we can get a quick benefit for fairly low cost. Of course, the disadvantage of this is limited controllability. Since those test vectors are very monolithic, they're not aware of each other. They don't use all the goodies of PSS that has to do with data dependencies, resource management, resource allocations, things like that, so we get less benefit. But it's a good start. So essentially, the biggest disadvantage is those models are unaware of each other. They cannot interoperate easily. So then, as the time progresses and adoption grows, SoC team now actually owns to refine those details, to actually make those activities or actions be aware of each other. So now we start refining those PSS model pretty much by doing what I've shown in the previous slide, by adding this keyword activity and expanding my basic simple test vector into something much more elaborate, much more detailed. And then, of course, I can start leveraging the full power of PSS to facilitate controllability and interoperability between those different scenarios. So benefits, the disadvantage is IP team still doesn't get any benefit. And Matthew explained what are the benefits for IP teams. So then, obviously, the next step is when adoption grows even further than that, individual IP teams are more motivated to own those IP level models, because now all of a sudden they can use, for example, the features of PSS for device programming, so they can verify or co-verify how those IP react to software sequences very, very early in the design phase, and then they just supply those IP models to SoC team instead of the beginning where they were supplying just test vectors. Now IP teams can actually supply SoC team with full-blown PSS models that can be reused across the company. So that's pretty much the flow, how we see it happen in a real customer's environment. And what it lets us do is essentially deploy this technology in piecemeal approach. It was very hard to take, large organization and just switch it to PSS in one day. And this is how it's done. So this is a full picture. I will not spend a lot of time on here. So this basically shows how some additional details of what layers they are. It starts from test realization layer. There is PSS core library, which is a huge addition to PSS 2.1. This PSS core library allows a lot of different functionalities, which has to do with executor management, memory management, and also PSS RAL. Methodology library is something that we work together today in Accellera group. This essentially a layer on top of PSS core library which accelerates test creation. And then we have IP level models, subsystem level, and SoC level models. Another important thing that I would like to highlight about IP level model is that today there is a few domain-specific libraries which essentially replace your IP level models for applications which are frequently used. For example, coherency and RISC-V. There are some ARM-specific libraries. So instead of developing your own, you can get some domain-specific libraries off the shelf to shorten your development cycle. So one example of how we model cross-IP flows with PSS activity statements. We begin with our SoC model, a bunch of actions and a bunch of rules that, like I described earlier, describe the rules of the game. And then we can compose those really advanced, tricky to create scenarios which also can be specified partially. What I mean by saying specified partially is that if we look at this video scenario, which starts with camera capture, continuous transfer of DMA, and then we decode to display and do show, in this scenario there's a large number of details that I haven't disclosed. I didn't say which processors are going to program every action here. I didn't say which memory they're going to operate on, and so on. So there's a lot of details that the tool needs to fill in to actually construct a scenario that is executable. Another scenario, audio scenario, we simply use a repeat. So we do 3 times in a row, we receive in a modem, and we play it. And then we can continue this activity. So that's essentially hierarchical way of thinking about our scenarios. That now I can take those existing scenarios, video scenario and audio scenario, and schedule them in parallel to create a system concurrency test case. So what the tool does in the background, it can focus on certain memory areas, it can randomly distribute on available cores, and the key outcome is that all those scenarios are correct by construction, and this is essentially what yields this productivity boost that Adnan was talking in the beginning of the presentation, that people spend way less time debugging their test case and spend way more time debugging RTL, which is exactly what we want to spend our time. So this is how we accomplish this, one of the first challenges of generating complex and valid cross-IP traffic patterns. A few words on coverage. PSS coverage, in terms of value add, what it does in terms of what we could not do before is, first of all, portability and abstraction. So PSS coverage is abstract just like PSS language is. The key difference between this and SV coverage is SV coverage, just like a Verilog, is very centered on kind of transactional signal level of whereas PSS is more system level oriented. So with PSS coverage, I can start asking myself questions. Have I seen activation of those 2 firmware APIs together? Have I seen this type of DMA transfer happening while a chip frequency switch happened? Predictability is another huge value add. So now we can optimize our regression suites up front. And it enables a number of really new methodologies and flows that people literally could not even hope or think 3 or 4 years ago. In particular, it has to do primarily with applications on fast platform silicon, where observability is very, very low. And it's fairly cheap to deploy because most of people who were already exposed to system level coverage in the past, the kind of mathematical mechanism behind system level coverage and PSS coverage is the same. It's just the description of our coverage spaces in terms of cover points and their crosses. I want to say a few words about memory location consistency in PSS, because that's one of the key challenges that I was mentioning earlier. So PSS defines the rules and also a set of facilities in the language which lets you model memory. So what we see in this example, we define a action that claims a memory from our address space with a size of, let's say, 20 bytes. And we define a contiguous memory space with 2 regions. I have a size with 50 and another one size 10. Then, if I have an action which repeats this my operation 3 times, there's no issues here because they are executing sequentially. Each one of them can grab a 20K size of memory and continue. But if we're running sequentially now, PSS imposes a number of rules which restricts allocation of memory for concurrently executing activities. And now, since I do not have a contiguous area of memory with 60 bytes, I will get a memory location failure here. So basically, the tool prevents me of consuming more memory than my design actually has. Last example is about unification of scenario space model across environments. So in this situation, we want to move from environment where I only have registers to environment where I now have software drivers. So what is happening here, I have this action TXUR data, and now we can extend this TXUR data to provide 2 different implementations of exec body. One exec body is written using PSS procedural style of execs. So here we're writing into registers. whereas the other exec body is using a template-style exec, which was described earlier. And here we're already using some firmware APIs which drive exactly the same behavior. So the idea is here that we have one logical structure of the action which captures the test intent that we're talking about. And now we can start extending those actions and providing different flavors of the exec body which implement this exactly same behavior on my target platform. And this, by doing so, we address the other challenge that I was mentioning earlier, and that is the reuse of abstract pieces content when we transition from register to driver-based testing and back. So to summarize, there are 5 key areas where there's benefits for SoC verification engineers. One is productivity, second is abstraction, reuse, quality, and coverage closure. Thank you.
So I have a general usage model question for portable stimulus. That is, if you expose all the low-level detail, then your stimulus is no longer portable. But if you don't expose those detail, then you don't have all the syntax to describe a specific scenario. So I've been struggling with this for 2 decades. I want to know what's your recommendation, and I have a question for you.
Okay. If you don't mind, I'll take the answer to the question. So that's why we separated out the 2 layers, right? The abstract layer is portable. The realization layer is not. So for a IP level, you need to specify a lot of details in the realization layer, but the abstract model is still portable when you go to a different implementation with a different level of detail. Okay? All right. Prabhat will take over, and then we'll have more questions at the end.
I'm Prabhat. I work at AMD in a methodology group. We call it virtual bring-up/shift-left methodology. We work on emulators, virtual platforms, portable stimulus, and these days AI too, somehow. I work with these guys on the portable stimulus Accellera work group committee. So I'll be talking about post-silicon testing in this section. How many of you here help post-silicon teams in some way? Okay. So if I say something wrong, please stop me or ask questions, because I'm not the expert. I work with them. And these guys, Matthew, Tom, and Adnan, they talked a lot about what are the different benefits of PSS. I don't think I can add a lot to it, but I'll bring some perspective for post-silicon with the personal experience that we had by using it in post-silicon and demonstrate all the benefits. So I'll start with what are the different goals of the post-silicon testing team are, and I'll then eventually focus on the first one. So when your chip is back, probably untested, unfused part, you want to do early bring-up. And so you want to screen for defective part. So usually your chip comes untested, packaged as soon as it can be made in the lab, and you want to make sure it actually works, it's not defective, and then you want to ensure some of the major things are working. That's your early silicon bring-up, and then you go to the next step, which is you want to try to do a systematic coverage of your features. So usually the post-silicon teams will have test plans and kind of directed types of feature by feature do the testing. And so you can isolate that each features are working correctly. Then you want to move on to a lot of stress testing. You have A0 silicon, and you want to make sure you find all the bugs before you go to your B0. So you want to gradually build up your test complexity. And cover, like Sergey was saying, a lot of concurrent testing, power management, frequency switching, all that. You want to create it in the lab. Hopefully you created before going to the lab and tested it on emulators or whatever fast platforms you have. Then you go to what's usually, at least at AMD, we call it all features enabled. You actually run production software and do your testing, qualify, measure power, performance. It's very hard to debug when something fails there. Then you go to high volume manufacturing, and there you want to optimize yield. Maybe you want to run some tests and vary external parameters for like temperature and maybe switch voltages and figure out a set of tests and parameters that optimizes yield. And this is a very complicated process. I'm not an expert in that. Or create a very optimized set of tests that will find the defective part as quickly as possible. Because post-silicon is where, when you go to first day bring up, people say, hey, we booted OS. And then you'll see this chain emails of, excellent work, thank you, good job. So people get very excited about post-silicon because that's where you're closer to the money. That's where you can see, you can sell your chips. By the way, I have missed a very important goal of post-silicon here, and that's the quiz for the end of the presentation. So if any post-silicon guys can figure out what's the very important goal missing, you'll have a secret prize by Tom.
He's going to buy you a cup of coffee.
Yeah, make it himself. So I'm going to basically trying to convey that using PSS language actually enhances your post-silicon efficiency, testing efficiency, as well as the quality of your overall post-silicon testing. So here are some of the benefits, in my opinion. Reduced test development cost. So as Tom and Sergey were saying, you can pretty much reuse the tests that were created at IP or SoC level as is. And actually, we have done it, and many other companies have done it. Run it on IP level, run it on your virtual platform, emulation, and post-silicon. The second point, in my opinion, this is the biggest benefit of PSS, where you're concisely capturing the test space of your IP and the whole system. This is where I feel like an ideal state will be where firmware or architects, they write the high-level PSS model. That way you have a very formal way of knowledge transfer with maybe very high-level actions, or you can go very detailed at the IP level. No confusion. This is exactly what this IP does. Tom will talk about more. We have a very big enhancement coming in PSS 3.0 with a very comprehensive way to describe coverage of the test space. Very big benefit. A lot of time, if you see the failures, maybe Sergey was saying in 2 weeks, or Adnan, you have a failure, they're running in a farm of servers, and 2 weeks you get one failure. Extremely hard to debug this case. And it's extremely hard no matter what you do. You can get that. But one way to mitigate some of the risk would be, well, we have this Lego block-like way of creating tests. And what if you can gradually create complex and less complex tests and kind of mimic the real-world scenario? And then maybe you can find the failure and bring it back to your pre-silicon environment for a debug. So your debugging, which is extremely complex process, a lot of time, Tiger teams will be formed to debug one issue that nobody can solve. This helps with that process. This is the new one. Use AI. Well, everybody's using AI, so you must. PSS really allows you to think in terms of test space. Like, DMA has n number of channels. It has some requirements on alignment of input data or input a memory buffer. Those are the things you're thinking. Those are your control knobs. So you get a lot of control knobs when you go to your SoC level that can allow you to really find the set of tests that, based on historical data, finds bug. So this is, in my mind, a very good use case for AI. In fact, I'll say you should use AI to help our constraint solvers too. So I'm going to go on that first goal, which is the early bring-up case, and talk about that. This is a simple AI accelerator IP where you have a 2D array of compute engines followed by some memory tiles and then some shim tile to connect to your rest of the system and a control processor to manage and execute program in there. So it's a very challenging thing to test in the post-silicon. There's too many paths, too many ways the chip can be defective or bugs could have escaped in pre-silicon. So you got the chip back day 1, day 0, whatever you count. What do you have to do? You got to make sure you can power it up. You can do proper reset clock sequencing. Then you want to make sure your major data paths are covered. You can do DMAs across, run on all the compute engines. You want to get the report of what you did, so you can say, okay, I'm done with the early bring-up. So for first thing, You may want an ability to create a lot of tests. Maybe the chip is not working. You don't know what the problem is. Do you want to experiment? Probably in the lab, because in simulation everything will be working. Simulation is not defective. So increasingly these days, the DFT structural test don't find all the issues. They still can be defect. And I would say that the building block approach of PSS allows you to do this more succinctly and get the benefit of what other teams did for you earlier in pre-silicon. So let's take an example of just booting this, initializing this IP. So usually the control processor will come up first and it will initialize the array. In the control processor, you'll set some TLBs, address mapping. You'll deassert reset, release some clamps, disable clock gating, and then you run the test. That's usually your simplified way of the boot sequence for this IP. So an IP team, they created a PSS model. By the way, we call it model because there's a lot of formal constraints. We don't call it a test or test bench. We call it PSS model. So here we have actions, set up the TLB running on the control processor. All these actions are running on control processor, release clamp, clock gate, reset. And then we created a base sequence that Tom was showing that you can, this is somewhat object-oriented language. You can carve out some of the base functionality in a base action. And then you have this boot array. So somebody, IP team, created this. I have an activity, which is a sequential block in PSS. I do set up TLB, reset, release clamp, clock gate. Simple enough. Then you update that model, and this is your test. So these are actions that will be used in the test. I've abstracted out some of the base functionality, but you have a register access test that's based on this base action, which is making sure the IP is initialized first because of this state input that Tom was describing. So I've set up those rules that if somebody wants to use this, I'll make sure that if somebody just picks this action, he'll get a complete test. Then I have an action that set up a circuit, maybe for DMA. You have, there are various ways you can do DMAs in that, but you have to set up the circuit or packet configuration. And then you do the DMA. This is normal DMA that everybody talked about. It will take a circuit state as an input, meaning it depends on this action that's setting up the circuit, needs the source tile, destination tile. So the IP team built up this model. This is one of the early bring-up tests. I just want to access registers in all the blocks. Okay, do the register action. So that's the exact line of code you write in the PSS. No more, no less. 5 lines. Then a simple data path test. Hey, I want to go through all the columns and do DMA. Again, a simple DMA test using this building block just for the early bring-up. Looks very readable. I don't need to learn about everything. This is a complete test. It will initialize the IP. It will set up the TLB, do the boot, and everything. So first one, this was the register access test. And this was the action that we put in the test in the 4 lines of code. It inferred this action because there was a dependency encoded in this action. So this is a complete test, and you get a test. For the DMA test, we just said, I want to do DMA. Tool inferred that you need to set up the circuit and give the circuits to the DMA, made sure the array is initialized and booted. Pretty cool. Actually, it's fun once you start creating more of these actions together. It's fun to create those in the lab itself. So you go to the lab, nothing is working. What do? Is the boot sequence wrong? Is there a defective part? What is the problem? So you need to experiment right there in the lab, right? You can't test this in simulation. So since this code looked simpler to some post-silicon person who had the knowledge, maybe not an expert, he said, well, I'm going to just move this thing which was at the top at the bottom and see if that works. So all these building blocks that are used here, they looked very simple, but I've omitted some things, right? there might be other rules that, hey, you can't do this before that, things like that. So the person who was modifying this code, or he basically extended the base boot action and created his own action. This is normal PSS. He didn't have to worry about that thing. Why? Because he knows, or she knows, that all the rules are there. If I did this, and this is not something allowed at all, the tool will figure it out and tell me, hey, you can't do that. But he wanted to experiment, so he created it. Fortunately for him, this was a legal case. So he said, okay, I'm going to create a new register test, the same register test, the exact same one. And I'm just going to tack in my boot sequence. And in earlier case, when this test was used, the boot sequence was inferred. But because this sequence also outputs the same state object and it has the same requirement for initialization, this all worked. And he got a test and able to test it. Similar for the DMA. The code looked very simple. I want to do parallel DMA and, well, now this time you want to experiment. I just want to isolate it to column 0. Pretty simple. I mean, this will be a little bit of education that the person will need, that, hey, this DMA action has some attributes that are user controllable. And that's what we call the test space. And this was one of the attributes. So even looking at the previous action, he could figure out that I can just do one column this way. And he did. And this worked. In fact, we used some of these things in a real example and found meta-stability issues, how the chip IP was powering up. So a big benefit, people sitting in the lab discussing workarounds, and immediately they're creating tests by moving things around, maybe in a graphical interface or very simple 5-line code. Very, very powerful to see this happen. Reduces all the turnaround of you going to architect, firmware team, SoC team, and this whole turnaround cycle is completely gone. So everybody talked about the language provides you all the means to do the right thing, but it doesn't just happen automatically. You still need to be somewhat disciplined, and so that's why you need some methodology layer so that, make sure your IPs can really interoperate. You have to agree on some buffer types, some state types as a company methodology. We are also working in the Accellera committee for defining some very bare bone methodology where you can get a PSS VIP or from a vendor and some other vendor, it'll all just work. So any action that an IP exposes should make sure that it puts all the rules that needed for that action. So a tool where people just can take one action or maybe two actions together, and that can give them a complete test. Meaning they should make sure it's dependent on IP being initialized, powered up, configured in certain modes. So that needs to be really thought through. That you want to have right control knobs for people and right rules encoded in the action itself, so that your users don't have to bother you. This is where the architects, IP or SoC, will come into the picture. They can really describe, rather than writing Word documents of 100 pages, they can use very high-level PSS code and just really describe their use cases in code. There's no confusion. And this is possible. The language is not too hard to learn. At a company or industry-wise, we do need a common, very thin PSS methodology library that we are working on. So these are the things, if we follow this, the rest of the benefit comes by default. You can do very comprehensive feature coverage because a lot of time when you're writing the actions, you are letting the tool explore the test space, and which is slightly different than UVM transactional randomization, rather than you're randomizing your whole test space. That includes your data randomization, control flow, everything, right? And with all the PSS coverage that's coming up, and that's already there, you can really generate a set of tests and look at the coverage without even running the test, what I'll get, and optimize your regression. Deep expertise, not everybody has to learn every detail of the IP, which is a big benefit in terms of documenters. You can truly build, mimic a real-world scenario with all the actions, and easily then exercise, stress test your IP, debug the problems on emulator. You can optimize your yield, select a good setup test, that an environmental condition that lets you categorize your chips in different bins and get a setup test that quickly find your defect. Big benefit, directly correlates to money your company will make. This slide I did with ChatGPT-4. I think I've said everything. There's no need to say it. I'm done.
All right, any questions for Pravat? Yeah.
So, being in a validation space there, right, I'm assuming that when you leverage the PSS model and test, right, in validation, so first you already have those tests qualified in simulation, emulation, whatever space. So most likely when you end up debugging it, is more rather than the functional, you are kind of debugging more of a structurals or metastabilities. That's the one confirmation. And then second thing is, now if you want to basically change your sequences model, then before even trying to silicon, you just make sure you regenerate the test case and make sure it works in simulation emulation. Just wanted to get your opinion.
Yeah, so for the metastability case, yes, obviously those tests were run in simulation, but didn't find anything. So yeah, just the ability to create more tests in the lab was very helpful. What was the second question? You run, I guess you can run only so much test in pre-silicon, even if you have emulator. That's a very expensive resource, and so you have to pick and choose. The methodology is allowing you to easily create a lot test than you would. Even in the post-silicon validation planning, if you see, it's kind of like directed, hey, I want to test this feature in an Excel sheet usually. I mean, pre-silicon DV is a lot better with all the automated coverage and everything. That's not translated yet to post-silicon, how systematic you can be about your coverage. And you can add all these randomization easily to post-silicon. So a lot of post-silicon people I work with, they're very appreciative of that. You can have all these randomization. You don't have to manually code everything. And then a lot of it you run in silicon emulation when you get the time on emulator, I guess. Yeah.
All right, so I'm having difficulty wrapping my head around how the portable part of PSS works with the post-silicon validation. So, for example, let's say I have a switch chip, and it's a largely dumb chip. It doesn't have a processor on it. It's not processor-driven, but it's just got multiple ingress and egress ports. So I've developed my test environment with UVCs connected to all of my ports to generate my traffic stimulus and send it into the chip, and I'm getting all the coverage. How do I take that PSS model and bring that into a post-silicon environment? Can I do that?
Yeah, that's my dream. Yes. So what you're describing is a chip that's more transactional or transaction-oriented, and you probably want to send random stimulus, and you kind of no expected output. So in post-silicon, you probably have some exercisers, right? Hardware-based. How do you control them? What you can do is take the same PSS model and control those hardware-based exercisers. The way portability works is in the PSS 2.0, we defined a register layer and a abstract memory layer. And we provided primitives to do reads and writes to the memory or register reads and writes. So that's the lowest point of portability. But maybe your case is not directly mapping to that. Your case is send a transaction, right? So you will create, your base layer will be send a transaction, which in UVM world will be driven from a UVC that has a sequence item that maps to your transaction. In the post-silicon world, that's some exerciser from Agilent or whatever, some company. And you will map that, how does that hardware actually does that minimal transaction, the external exercise.
So is the expectation that I will be able to take my portable stimulus model and directly run it on some hardware generator?
Yeah.
Natively read that and generate the same traffic patterns?
There is an integration effort, right? You have to map your basic primitive concept, which in your case is more transactional than a processor programming type of interface, to that hardware environment. Right?
Remember, the portable stimulus model itself doesn't actually execute. You have to use it to generate an implementation for your target. Okay, so you're going to have whatever is going to be at the top level telling all those hardware things to send data in and out of the chip, as Prabhat just mentioned. Right? How you do that is the realization layer of your model, and in the early stages, you'll have the same model, and your implementation will be UVM. Right? So we can talk more about that later. We got another question over here. Yeah.
Okay. The final question is about as for post-silicon, the packaging, interconnect of different die. The situation, even the design for test, is not that mature. So as for post-silicon, the interaction between different dies is another challenge. That in emulator or simulator, the functionality could be verified well. However, as for the manufacturing perspective, PSS is valuable to exercise the design defect. So how, just thinking how to debug, and the PSS just find the corner case on the manufacturing perspective, especially on advanced packaging. Is there a mindset?
No silver bullet here. You're saying you have a good set of PSS model or some test library, and you had a manufacturing issue, and how do you debug that? The way I would do it is
really good tests which PSS gives you, and the rest of it's up to you.
Yes. I would do the process of elimination. Start with very, very basic test and gradually build up your test and try to do a binary search in that way. So the methodology will allow you to do that quickly. You don't have to go talk to the IP person or... So just the ability... Actually, it gets a lot of fun to create those tests in the lab, which doesn't really happen much.
All right. Hey, thanks.
Thank you.
All right, so I'm going to wrap up really quickly. Here we go. What's new in 2.1? Look at last year's tutorial. Okay? So we have all these things. So test realization, we talked about the memory and register enhancements. We talked about some activity modeling, some things like we can specify certain regions where you don't infer actions in the middle, added labeled anonymous transactions, things like that. So all of this was detailed in excruciating detail last year in 2.1. Few more things, particularly remove C++, floating point data types, some I/O and messaging, and some randomization stuff. This is the big thing coming in 3.0. As I mentioned, scenario level coverage. So the idea here is that given a stream of action executions, we want to find out what the temporal relationship is between certain things, right? So when you specify a portable stimulus model, you can say, I want this to happen, then this, and then these two things to happen in parallel. Okay, what does it mean to happen in parallel?
There's a bunch of
the semantics of a PSS model are that they have a common predecessor which must complete before either one starts, and they must both finish before the next one goes. It's kind of like a fork join in System Verilog, right? When you actually go and run that test, okay, depending on how your system is set up, those two things may or may not overlap, right? Even though they have the same predecessor and successor, if you have a single-threaded system and you're doing two things, quote, in parallel, you're going to start one and then do the other, right? That's kind of what happens in a fork join. What you want to be able to know, though, is if I have multiple threads, did these two things literally overlap? Did one start before the other one finished, right? So we need to be able to define that, and we've added those kinds of things into the language. It looks very much like an activity, but it's different. It's not an activity. It's something we call a monitor, and you specify a cover statement on a monitor to define these behaviors. Certain questions you can answer off the bat, right? If I say, do this and then do that in my activity, right? A followed by B, and I ask, did A and B overlap? The answer is always going to be no. So certain things we can tell just by looking at the model. Some things we can't answer until we actually run, right? And so part of what we're doing is defining the semantics for that and how we understand what that means and how we can then capture that in some sort of a coverage database, right? That part of it is not part of the standard. The standard says if these two things wind up overlapping, you need to record that, and then that's up to the tool to figure out how to do that. So this is how we do it. So in this particular case, right, I want to say, did I do a write followed by a read? Okay, so this is the set of things we have a write here. Once that write completes, then we start looking for reads. And it turns out that there's two of them. So there's two matches. And then we have additional semantics for saying I want the first match or I want to figure out when one of them matched. We can put constraints on it. Right? Did I read from the same address as the write and things like that. So there's lots of things we can do. That's all in there. We'll probably go into a lot more detail probably if we do a tutorial next year, which we may well do. It might be a workshop next year. Who knows? But that's what we're talking about. So with 3.0, we have reached feature freeze. We are working on reviewing the documentation, particularly this whole new chapter on behavioral coverage. Our expectation is that probably at this point, maybe by the end of March, early April, we will actually do a public review. So we will issue a version of the standard for a 30-day public review period. You'll be able to download it, look at it, read it, go through it to your heart's content, and give us feedback. That's going to be really important. We want to make sure that we do that. Okay? We did this for the initial portable stimulus spec. For 2.0, we didn't do it because the things that we added weren't they were really good, but they weren't really earth-shattering. This, particularly behavioral coverage, this is like brand new stuff. So we're actually defining that. I would like to call out Dmitry Korchemny from Synopsys, who did a lot of the work on this. And so the rest of us have sort of been trying to catch up to him and understand what the heck he was talking about. But I think we've got it to a state where it actually does make a lot of sense, and it's something that people can understand. But we want to make sure that everybody else really believes that as well. So we're going to do that coming up probably, like I said, late March, early April. All right, so again, the whole idea here is to raise the level of abstraction of what's going on here, right? We want to think about scenarios, not just right? In UVM and system earlier, we went from thinking about pin wiggles to thinking about transactions, and now we want to think about scenarios, right? So we also don't want to focus too much on implementation when we're talking about the model, and we want to be able to think about these things as executable documentation, right, which we're doing. So you have the PSS model, you have your target-specific realization, and then your UVM environment is a good target for that, but as we mentioned about, it could also be other things. So we really are talking about block to SoC reuse here, right? And I actually had somebody earlier ask me about, well, I'm a post-silicon guy, and I think this would be really cool. How do I get the IP block guys to do this, right? We've been focusing more on convincing the IP block guys that they have to do this because it'll help them, even though there's going to be a lot of benefit down the road. But we got to get them started. If we can start at the other end and convince those guys and get them to push back, that's going to be even better, right? So we can easily capture IP-specific knowledge. So we talked about the different ways that you can create these things. We can compose complex scenarios, right? The PSS models are hierarchical. You can infer things based on the rules. And then the model gets implemented on your target platform, however you need it to be, right? So lots of stuff going on there. I hope that this gave you a really good understanding of what we mean by portability, what are the different pieces of a portable stimulus model, how breaking it out into an abstract model and realization layer is really what gives us that portability, and the benefits that you get from it. Okay? I learned a long time ago when I started doing Superlog way back in those days before System Verilog, our CEO said, we need to understand that we have to sell the value of what you can do, not how cool the language is, right? And it's really easy to get hung up on how cool this language is, and the same thing has happened with every language that's come before. And yes, this is a new language, but it really is not that hard to learn, right? The guys that I talked about earlier that found a bug in PSS without UVM, they said that it came up a lot faster than they thought it would, and they were able to do a lot. Adnan also mentioned the data that he's got, right? It really literally takes you savings of 50%, including learning the language, to do this, right? It's really not that bad, right? System Verilog is, 1,500 pages? This is, I think, once we got rid of the C++, we're down to like about 600 pages or so. That's really not a lot. And you don't need to know all of it to be able to do cool stuff, right? If the abstract modeling part is one piece of it, the realization is another piece. It's kind of like UVM, right? There are certain people that know how to build UVM environments, and they know the details of how sequencers and drivers and all that stuff work. And then there's test writers, right? It's going to be the same kind of thing. Nobody is going to need to know all of PSS. You're going to know what you need to know, and we've set it up to make it easy to be able to share that knowledge as you go through the system, right? So that's kind of where we're at. So I would like to bring up all of my co-presenters, as well as Hillel Miller from Synopsys, who's also a member of the working group. All right, who's got a question? Yes.
I'm curious that because PSS is an abstraction over UVM, so what are the overhead assessments going on in terms of compute requirement or additional overheads, time overheads, adding PSS?
Right. Anybody want to take that one?
Sure, I can. I think it's faster. I think in a lot of cases you can pre-solve the transactions that have to go into UVM. And I think because we can plan all the scheduling before we start the run, I think we do a lot less work than solving in UVM.
You guys have touched on stimulus and coverage, but you haven't talked about the other part of verification, which is the checking. How do we know that the data is doing the right thing? Does PSS give us anything for that? And is it portable?
All right, Matthew, you want to take that one based on our paper from 2 years ago?
Yes, PSS has features for checking. Oftentimes you want to abstract away your checking as well. If you think about doing your detailed block-level checking at SoC, there's overhead there. So oftentimes you want to focus on a lighter weight test checking that is portable, and at every level do more detailed checking that may be a little bit more environment specific. But I guess fundamentally the language definitely does have features.
Okay, over here I'll completely contradict Matt, and hopefully you'll forgive me. PSS has support for data structures, right? So we can store expected values, and we can do checking. And I think the reason being able to synthesize the checking is important is to be able to move it from simulation to emulation to post-silicon.
Yeah, so maybe just to add to it, there are certain patterns in the language that are known and deployed that capture reference checking for modeling as part of the model itself. And by doing so, you basically abstract away the checking as well. You don't need to rely on scoreboard and UVM, which all of a sudden not available in your emulation environment, for example, and capture the key checking aspect in the model itself, primarily using flow objects.
All right. So usually with UVM, we'll launch different V sequences or whatnot during different phases. How does this interact with UVM phases?
Has he? Right. Yes. Okay. So the question was on different UVM sequences, different phases. Okay. So you're talking about the different runtime phases. Yeah. Okay.
So PSS is primarily a stimulus language. So wherever your stimulus runs in whatever phase is where you do stuff.
Right. So this is why I spent the last several years telling people only run phase. Right. But if you're
you can. I mean, I've done a lot of experiments where you can synchronize UVM phases with the generated test. There's ways of doing it using events, and sometimes it comes up the need. I mean, sometimes you build a test bench in the build phase based on some randomization of your configuration, right? So, number of agents. So that's possible.
Yeah, the intent will remain same. It's how you then construct the test bench. Maybe tool-specific, integration-specific.
Question for Prabhat. What were some of your challenges with enabling PSS in post-silicon? Did you inherit the models from the IP teams, or did you go the other way from silicon to the IP teams?
I'm going to cry. So, this is a new methodology, completely new language. Generally, people don't want to spend time on it. A lot of time, the IP teams or SoC team, they are in their cycle of next projects. So the way we are approaching, at least, is have a separate team like us, which is a methodology team, but more hands-on. Work directly with teams where we see an immediate value. For some project, we saw there is a need. and we can fill some need which goes from IP all the way to post-silicon, and that's where we focused on. So find a need, help the projects now, and then gradually build up the library.
So you mentioned that the constraint in some DNA transfer. Okay. So is it current PSS supported some temporal space constraints such as the specified some the throughput, maximum and average, something like that? And second question is that the drawback of the such as the top level, the compiled driven one is that there are some very difficult to debug that from the generated C code to where is the exact some original source code is. Is it in your experience? Is it easy or has some difficulties?
I apologize.
Okay, so I think the second question you asked was how can you go from the generated sequence back to your PSS code? Okay, so that's a tool issue. Okay, that's so I've mentioned this to a few people here already. So there are certain things that we can put in the standard and certain things that we can't. That's one of the things we can't, because the important standard is to allow vendors to compete and to allow you guys to push the vendors to do the best solution possible for whatever your application is. Okay, so we can't put too much in the standard because then that limits the amount of competition that can be done. Right? So the standard does not talk at all about correlating the implementation back to the original PSS code. That's a tool issue, and the tools that do that better will be more likely to be successful. Okay, so that's that one.
But there are things that we can do in the standard to make that easier. For example, a canonical naming convention for action occurrences. So when you see in the generated test an action occurrence name, if there was a convention, it'd make it much easier to go back to the original code and figure out where that action is coming from. So there are things we can do in the standard.
Right. Okay. Yeah, but that's to make it easier. That's not to solve the problem, though, right? Yeah. So okay.
But it is reasonable to expect that it would be possible to take your actual run, including on silicon, which is much more tougher to do than in pre-silicon, and back-connect it back to the source PSS code.
Yeah. Okay.
Did anybody get my quiz?
Yes. I was wondering about that. I thought not to bring it up.
Security? No. Well, could.
We can have two more questions.
Okay, so we talked about the portability and all that. I have a question about what is the recommended thought. Let's say we have a block level test bench, we have a subsystem level, full chip level. So what is the recommendation? Like all of these levels will have individual models, and how we reuse them and make it like scalable, or what is the process basically? Like, what should we do?
Okay, what you should do is go back 3 hours and listen to the entire presentation again.
Oh, poor guy. The idea is that you build models for each of the IPs and then compose those IP models into the system models.
Yeah, sorry. Same way you build up a level UVM and then put those environments together for system level, right? It's the same kind of thing. It's just that with PSS, it's actually easier to compose them that way because of the way we set up the language. Right. So, okay. All right. Last question.
Make it better. Each, one language exposes the weakness of the other one, right? Now, PSS, the memory handle, right? Especially the value of the address location and things like that. It's not there in system Erlog, right? Do you foresee that gets implemented in system Erlog, or you don't see the need at all since PSS supports it?
Sorry, what's the question?
Yeah.
Okay. So I'm talking about the memory handle, the pointer, right? System Erlog does not have that. But right now you can allocate the memory block. You can take the handle, which actually returns the value of the memory location. I think that's what, right? So that doesn't exist in UVM, which is very powerful. So do you see the need it can be implemented in UVM, or be in the UVM next rev, or a system Erlog next rev, we can actually implement it, or you don't see the need?
I see the need to synthesize checkers. Sorry. If I'm thinking about new feature, I'm thinking about PSS, not system Erlog. But yes, it could be very helpful. We had to invent the memory allocation, because when you're composing an activity which has a lot of parallel blocks or schedule statement where a tool might choose some concurrent operations, and you're using some of the building block actions from IP, for example, the action that Tom was showing, the chain DMA, with a lot of memory allocation going for a descriptor itself and for the actual DMAs, right? If you compose that in a bigger scenario, it's going to be very hard to manage the memory allocation in PSS itself. So we had to do that just by need, because of the tool can schedule things based on the rules anywhere they want, and we need an easy way to allocate memory. So that's why we did it. I mean, it's possible in System Verilog too.
Yeah, but the thing is, if you can go from a PSS model that deals with all the memory abstraction, and it comes out with an actual address for your system, given the rules that you've given it, then just use that in System Verilog. Who cares? Okay. So with that, I'd like to thank my co-panelists, and thank you all for coming. We have a few minutes before lunch. Run up there and get in front of the line. All right. Thank you very much.